join. Three data. So we can have a login errors, we can be minimized. Minimize this will be small. So we can have a look there sometimes if anyone they want. I think no one is asking online question. And
they ask it, so we kept asking.
Simply dummy. Two places random message will show. But we also log in. Our end we should
check RRA. Okay, go to session.
Chalo. Started, huh?
So the first row is missing. I mean, should I start anyhow? Are they coming or are they coming? Okay. Okay, so I guess now we can start. Okay, so what I have prepared for today is first one is written over here. I mean, I want to discuss the hydrodynamics of driven lattice gases. I mean, that of course is rather similar what I had before, but you will see it's a different equation, and we will have different macroscopic behavior. I mean, so to some extent it repeats some idea we had. And but there are new phenomena which appear, and then the second part of the lecture will be sort of like I mean, what I sort of call the poor man's statistical theory. You see, after all, the limit equation which we have, the hydrodynamic equation, is a perfectly deterministic dynamics. In fact, it's really a law of large numbers. I mean, whatever you do, I mean, if you look at some sufficiently large scales, you will see the same macroscopic behavior. But statistical mechanics, statistical mechanics by definition also wants to understand a little bit more about, what are the statistical properties. I mean, wants to go beyond the law of large numbers. And that sort of usually, I mean, there's a rather simple theory which goes back to Landon-Lifshitz and which sort of avoids, extreme microscopic details, and that will be the second part for today. Okay, so then let's first think about what I've written up here. I mean, and of course it's the usual setup. I mean, I have these weights for nearest neighbor jumps, and they somehow depend on the entire configuration. And of course, I mean, the computation which I did before yesterday, I mean, computing the current, I mean, there's no difference. I mean, so the current function between x and x plus 1, I mean, between the two sides, is equal to the corresponding weight. And then I have to multiply with eta x minus eta x plus 1. Okay, so this is sort of course, not really changed at all. But now we have to compute the steady state, right? And then, of course, abstractly, we know the steady state is the transpose of this generator is equal to 0. So this is the steady state, okay? Now, the first observation is that since we have a conservation law, there will be one parameter family of stationary state. In each sector, of course, there will be a stationary state. And now you might think, okay, now you get some very complicated structure, but then there's sort of a funny theorem which tells you that what we use from equilibrium statistical mechanics, namely, what people call the equivalence of ensembles. I mean, the fact that when you look at a very large system, and let's say, I fix the number of, I strictly fix the number of particles in my large volume, and then if I make the volume even larger, eventually, we can go over to the grand canonic description where the density appears up in the exponential. And, for a large system, we will get the same results. That's sort of what is called the equivalence of ensembles. And there's some similar result over here. And that's useful because while it sort of is not an explicit formula, it gives you an explicit dependence on how the density appears in the steady state. And so the result is the following: is that I mean this rho S can be written as a normalization, which I don't display here, times e to the minus h of, I call it h bar, that you sort of don't confuse it what it before. I mean, of course, any probability can bite off the exponential of something, right? But here the claim is that we're looking at a large system, and we don't want to have sort of in this exponent, we don't want to have things which sort of have dependence on things which are far apart. I mean, so this has some sort of locality property. I mean, that's the reason why we like to look at the exponent rather than at the function, right? I mean, there it's sort of more this product structure, but here it's a sum structure, and that's sort of, we don't know what the h bar is, but the claim is that there is an h bar with decent properties. But now the main point is that when we start varying, then it comes in sort of exactly in the same what we are used to. I mean, so there's a chemical potential, and then we have a sum over x, and then we have the eta of x, right? So the only difference from the detailed balance cases, for detailed balance, of course, we know exactly what this object is. But here, it's just sort of abstractly given, and in concrete examples, this question was asked already, and then the answer is the same as 2 days ago. I mean, people have not really worried, and then there's no real sort of theory which would allow you to systematically determine what this object is. But in principle, there could be one. I don't know how interesting, how much people have really spent time on it. Anyway, so now of course, I can just repeat what I said. I mean, now we're looking at slowly varying initial states. I mean, so, I get chemical potential, which is depending on the position and has a slow variation. And of course, we have the conservation law. And so what I said yesterday is just exactly the same as before. So we have here now the time change of eta x. And now I put the t here in the distribution, in the average, and then there's sort of a initially discrete derivative, and then I have sitting here, well, I guess in this notation it's a minus, and then I put here an xx plus 1. I don't know why I wanted to do it like this. Well, anyway. Doesn't make any difference here. Well, no, I think this just is a misprint. I mean, so, and then maybe I should put here x minus 1x, okay. Okay, and this is also at time t, and that should be equal to 0, okay. And now, you know, what I said is that you know, this is presumably a complicated average, but then we assume slow variation, and then, you know, this complicated average can be replaced by an average of this type, where I just adjust sort of the chemical potential. And so, so here I do sort of the hydrodynamic limit. And then I get the ddt of this is not the density, so it has nothing to do with the rho s. I mean, this is the density of Q and T. This was my notation. And then I get here the dq. And then I get here some nonlinear function. So now, of course, you know, there's no argument why this current should be 0. And we will just see in examples that, of course, it's non-zero. And you know, the precise specific form depends on the model, but the point is it is some function of the density, and so the equation which we get is then this is a function of Q and T, some nonlinear functions equal to 0. Okay? So this is with the same arguments as I sort of tried to explain yesterday, is sort of the corresponding macroscopic equation. Now, of course, this is now living on a much shorter time scale because you see, you know, we only have first derivatives, and so it's sort of more like a ballistic motion, whereas yesterday we had second derivative with more like a diffusive motion. So typically, you know, here I will have traveling waves rather than sort of things spreading out diffusively. Okay, and now maybe we should sort of recall what is the current density function. I mean, that's sort of now the sample object, and so you have you know, you have rho. I mean, so okay, so now I'm seeing that you know that there are always sort of too many rows sitting over here. I mean, now okay, so okay. Let's see, where are we? Okay, so here we have the mu, and then of course, you know, just like we had before. I mean, the mu is connected with the density, and so what is typically plotted is then, so density is just a parameter, you know, in the steady state, and what is plotted is then the density, which is between 0 and 1, and up here I compute what is the average current, and of course from this formula up here, you can see that we have the same formula as before. I mean, there of course was 0, but now it's non-zero, and I can just look at the jumps from 0 to 1, and then I have eta 0 minus eta 1. So it's just this current function over here. That's something, of course, rather explicit. But you know, if I give you the model, then I know this object. But then comes this average over the steady state with density rho, and that, of course, is something which we usually do not know really explicitly. Okay, so let's do, you know, the usual sort of simple example, which is called the RSEP. I mean, that's the asymmetric simple exclusion process, and of course, it's sort of the obvious variation. I mean, we had yesterday the SEP. I mean, in the SEP, you know, one was saying that you know, these exchange rates, they are symmetric. They are all, I mean, you know, either going to the right or to the left. They're always 1. I mean, so this would be 1, and well, let's do it like this, okay? And then maybe here's another particle which is going to the left. I mean, this was also 1, and this gives a symmetric situation. A symmetric situation, I mean, this current is equal to 0. But now we do easily an asymmetric situation by assuming that the jumps in this way, let's say, have the weight Q, and the jumps in this way, they have the weight P. And so there are two Q's. I mean, that's also the spatial variable, but it's two different things. And then of course, and then we come to the asymmetric situation if the right and left jumps sort of have somewhat different weights, right? I mean, that was part of the exercise class also. And this is the simplest case. I mean, I simply assume that these jumps do not depend on neighboring sites. And if you want to have more complicated cases, here for this weight function, I mean, then you should assume that this jump actually depends on, whether, the neighboring sites of the bonds, whether they are occupied or unoccupied. Okay, now we have to do this little computation here. You see, so I have given you, so maybe I first should write out the weights, I mean, just sort of as an exercise so that you see that this is sort of nothing very, very complicated. I mean, I have the weight P for jumps to the right. I mean, so I take 0, 1. So in order to have a jump, I must have a particle at 0, but there should be no particle at 1. So here I put 1 minus eta 1. And so, this is sort of non-zero only if there is a particle at side 0 and no particle at the other one. And then, of course, I have the other possibility that it's Q. And then, of course, it's just the reversing. I mean, there should be no particle at 0, and there should be a particle at 1. Okay? So it's that simple. And now when I can compute the current, I just have to multiply with eta 0 minus eta 1. And that's an exercise which I leave to you. And the next thing is I have to do the average. And for this, now you have to check. Actually, it's sort of a, I mean, it's not a very difficult computation, but it's a useful computation. And, a priori, it could have been more difficult. Anyway, I mean, what one finds is that the NES, I mean, the non-equilibrium steady state, is just independent Bernoulli. I mean, the obvious thing, right? I mean, the average, I mean, the etas are independent, and of course the average of eta is just the occupation. Okay? And so then you do this multiplication, and I mean, then you know how to do the average. I mean, for instance, the average of this one is, of course, it's just rho times 1 minus rho, and the other one correspondingly. And so I'm not working out this multiplication, but the result is sort of pretty obvious. So let me put it up here. So the average current from 0 to 1. I mean, first of all, it's proportional to P minus Q. So, it can have either sign. I mean, the current can go either to the right or to the left. And then, of course, it depends on the density in a quadratic fashion. And there's not so much to choose because, if I'm at density of 0, then there are no particles have a carbon. Then, if I'm density 1, then everything is completely blocked, so it has to be 0 also. So the only function which is left is 1. But this, of course, comes out from the computation, right? I mean, I'm just saying that, I mean, the result is not terribly surprising, okay? And so you see that for that very particular case, I mean, you have a simple density current function which simply looks like this. Okay? And now if you can do more exercises, I mean, you can sort of add interaction with nearest neighbors, and then maybe the nest is something slightly more complicated, but you can find examples that where you can still do the simple computation, and the result of this is that in general these functions can be quite arbitrary, right? I mean. In the sense that, here you have sort of this convexity, but all these properties are just sort of because of that particular simplicity. But, if I just take a slightly more general models, I mean, of course, what you all must have must be 0 and going to 0. I mean, that's sort of because of the exclusion rule. But what you see in between can be sort of really, quite, some function which has a complicated shape. I mean, depending how complicated I make the interaction, right? I mean, so you should not think of and of course, if I start having sort of somewhat more complicated current density functions, I mean, you might get sort of more sophisticated type of phenomena. But for these lectures, I will not go into this one. I will just look at this particular case here. All right. right, so now we want to think a little bit whether there could be other cases also. I mean, for instance, could be the carbon function equal to 0, right? Well, a priori, it's not excluded. That then you might say, well, you know, but how? So we didn't impose detailed balance. How could it be possibly 0? But let me just give you a simple example how this works. I mean, so we can assume that we do now. Okay, so here we had nearest neighbor jumps, and let's maybe take and now let's take jumps which can go more than to the nearest neighbor size. I mean, you know, I still have the perfect exclusion, and the jump doesn't depend on neighbors, but, you know, I can jump maybe, you know, 10 sides to the right or 3 sides to the left. And so let me give you so now we have jump weights. Okay, this weights, and now let me just give a general function p of x. And of course, these have to be weights. I mean, they have to be larger than 0, right? And maybe I don't want to have a very slow decay, but anyway, I mean, so I give you just, you know, the weight to jump from 0 to side x. Okay. So in our case, I mean, you know, I only went to the right and the left, and so it was a function which was sort of concentrated on 2 points, but now I can do more. And then you can ask yourself, if I now, so whenever you do this, I mean, then you figure out that the nest actually doesn't change. I mean, you know, it's always independent Bernoulli, so the nest, you know, doesn't care about this change. But of course, the dynamics does. And so you can ask yourself, for which choice, I mean, would be, for which choice would this system satisfy detailed balance? Okay, and then you see that detailed balance, yeah, it's sort of essentially obvious, but it's related to the fact that this function is an even function. That you check sort of by hand. And so now you see that the average current, the average current is, so to speak, the first moment of this thing, right? I mean, so the average current is something like the summation over x p of x. You know, that sort of jumps to the right and jumps to the left. And so you see that because this is an even function, then of course what we know already that in the detailed balance case it must be simply 0. But you can certainly construct functions for which this is 0, but not an even function, right? And so you see that in principle I could also have situations where this current actually vanishes. And that's sort of then a funny situation because you know, we have something which does not satisfy detailed balance. You know, the current vanishes, and then sort of, you know, the first order equation. I mean, the equation which is sitting over here. You know, I mean, this term vanishes, and then presumably all the phenomenology which I told you about, you know, going to the next order is presumably still correct. But you know, maybe not so, because, you know, after all, it's not a detailed balance system. Anyway, so I just wanted to say that, you know, the current function could be actually 0. Okay, so now let's see what else I wanted to say here. Yeah, okay. So now we want to spend a little bit of time in looking at equations of this type here. Now, of course, not too much time, but still equal to 0. And you know, I mean, on equations of this type, I mean, there's a huge mathematical literature. I mean, has been, you know, because. One question. Well, something is happening. Okay. Okay. So these equations are called hyperbolic because it's first order, and it's Yes, okay, what is the question?
Can you ask the question?
You can hear us?
Oh, okay.
You should unmute from here. Then. You can speak now.
Okay. All right. So, so as I said, I mean.
Yeah. I have just so the question was that when you did this hydrodynamics, where did the ballistic and diffusive scalings of the time came?
Through my words. So the point is that well, I mean, first of all, you know, now let me answer sort of more seriously. I mean, first of all, you know, when you follow the scheme, you know, and you start computing the average carbons, and then you do the first order density slope expansion, then you see that you know, these are sort of the leading terms in the hydrodynamic picture, right? And now, of course, you know, you can sort of do it sort of slightly more seriously. I mean, you can sort of, you know, assume explicitly parameters which sort of indicate the slow variation initially, and then then you have an extra, you know, as I emphasized, everything depends on, you know, the small parameter is actually the slow variation. So if you want to make a more precise statement, then you should introduce the parameter which gives you this slow variation, and then on the level of this parameter, you will see that you know, this expansion which I'm writing down is sort of okay. So if I take a small parameter which usually is called in this business is called epsilon, and then you know, in terms of the small parameter, you now can quantify at what time scale, you know, these various contributions appear. And so when you look at the ballistic scale, which is sort of time. So, you know, the epsilon is something which is sitting in the initial conditions. It's not something which is sitting in the weights. So, but then if you look at times of order epsilon to the -1, you will see the ballistic scale. I mean, that's sort of, you know, what I'm talking about at the moment. And then if you go to even longer times, so this is ballistic. And if you go to even longer times, so this is time epsilon to the -2, you know, it's just ordered by the number of derivatives. I mean, nothing very deep here. It's just saying that you can make this more quantitative. I mean, and then you have the diffusive time scale. And usually you don't go beyond. I mean, of course, in some cases, you know, people have tried to do higher order expansions, but that's sort of, to some extent, a dead road. I mean, so you know, beyond diffusive, things become sort of so model specific that you don't really want to use it anymore. But these type, I mean, these two distinctions are very useful. And so, you know, in physical term, what this means is that, you know, I prepare my initial condition that fixes the epsilon, whatever that exactly is, right? I mean, but you know, it's really the variation in the initial state. And then, you know, what I'm saying is that when you look at shorter times, well, if you look at very short times, nothing is happening because things are locally stationary. Then if I look at somewhat longer times, I mean, this epsilon to the -1, then I see the ballistic, I mean, the kind of equations which I'm discussing at the moment. You will see, you know, the effects of the hyperbolic conservation law. And if I then go to even longer times, you will see a small correction, which is diffusive. I will explain at the end of this section here. And, you know, in the reversible case, the carbon happens to be sort of completely zero, and therefore you only see the diffusive contribution. Okay, so I hope that explains a little bit more than. All right, so now let's see. Okay, so I want to, so of course, you know, I'm not going to give a lecture on hyperbolic conservation laws. I just want to say that, you know, because of fluid dynamics, you know, and then there is one-dimensional gas dynamics, and so you know, this has a long history, and of course people know extremely well about these things, and I sort of want to single out sort of essentially one single item which I always sort of found extremely surprising if you think in terms of, it's not so surprising on the level of the macroscopic equation, but it's surprising on the level of the underlying stochastic lattice gas. And so let me do, so now first I want to do one other thing before doing this. You know, but what you always like to do is you want to linearize. You know, it's a nonlinear equation, so maybe you linearize by assuming that you have a small deviation from from your initial data. So let's say the rho q of t is a background, which I call rho 0. So this is just a constant function, doesn't depend on time, it's not changing. You know, I mean, the constant function is obviously a solution of this equation. But then, you know, I take a small deviation, which maybe I want to call u. And then, you know, you have to linearize. I mean, so, you know, you just plug it in. I mean, then you get dt of u, and then you get, I mean, you know, the derivative of the current at the background density, and then you get dq of u is equal to 0. Okay. And so, you know, let's do this exercise for the RCEP, and then you see that this is p minus q, and then you get 1 minus 2 rho. And I just wanted to indicate to you that you know what this means in the RCEP is that you have this background density, and then I take a little bump. Then, you know, so let's say P is larger than Q, I mean, then this is positive. But you see that this is changing sign. So if I'm at this very small density, I mean, this might be going to the right. I mean, that's, you know, sort of particles sort of basically can follow, you know, the external driving. I mean, you know, I take P causes P larger than Q. I mean, so I want to jump to the right. But, you know, this can be, if I make the density sufficiently high, I mean, larger than 1/2, I mean, this is negative. So I can also go this way, which at the first sight is surprising, but, you know, if you think about it, it's rather natural. You know, particles are pushed, but they're sort of piling up, and then you get sort of the backflow, right? I mean, and then the linearized equation, you can see this immediately, that this both phenomena happen. Okay, but now I want to sort of look at a slightly more interesting initial condition, namely something which people call step initial conditions. Which you know, as the name indicates, is that you know, I mean, beyond the linearization, that's the sort of next interesting initial condition. And then, or what you do is you start with an initial condition which has a step, and then you're asking yourself what is going to happen, right? I mean, it's just sort of, you know, so people in physics would call this domain ball, but you know, whatever. I mean, it's just a step initial condition, okay? And now you wonder what's going to happen. And let's see, what did I want to say here? Yeah, okay. And so now clearly, if I want to specify the step, I mean, then you know, I have to give myself. So this is my Q. I have to give myself the rho plus and the rho minus. So this is simply the density of the right and of the left step. And now you can have actually sort of two situations. I mean, if I'm in the case which I plotted, I mean, so this is the rho minus is larger than rho plus. I mean, then you know, it's rather intuitive that you know, they sort of want to spread out here, and so somehow you're going to lose the step. I mean, the question is, you know, how will you lose the step? And as you know, very generic type of phenomenon, what happens is that okay, so you know, first of all, there's an endpoint of the region where I have the density rho minus. Okay, and this endpoint moves with a particular velocity, which at the moment I really don't care. But you know, I mean, it's you know, you have ballistic scaling, because this is sort of you know, if I scale space, I mean, you will see still the same step, and therefore Q and T are exactly of the same order. So this term sort of must go linearly in T. I mean, this location, and then the other location will be also linearly in T. Okay, but in between, I mean, you have some smooth profile which is interpolating, and of course, you know, when you look at your equation, I mean, you can sort of figure out, you know, if I give you the current function, I mean, then you can sort of figure out, what this interpolating profile is. Of course, if I give you a complicated current function, then maybe you're a little bit stuck and one has to do second thinking. But for this simple case, I mean, you can find in fact the explicit solution, and you find that but only in this very special case, you find that the profile in between is just completely flat. I mean, linear. I mean, okay. In general, it will be more complicated. It will be some nonlinear function. There could be, several things. And anyway, but for the RCEP, I mean, this is what happens. So that's about the simple thing, and not okay. Anyway, so of course, I mean, the slope will be 1 over t, right? Because this is expanding linearly in time. Okay, so there's a v plus of t here, and there's a v minus of t. Okay, so this is a simple case, and then the more exciting case is when you look at the opposite situation. No, this way. Okay, so this is what people were fascinated early on for these equations, that when you look at the step in the reverse way, so now I'm going to look at this particular case here. Okay, let's put this at silver. So I have this situation, so this is the rho plus, and this is the rho minus, right? And so now I have the rho minus less than rho plus. Okay, and now the question is, what is happening now? Now you see this naive intuition that particles sort of see essentially sort of a low density in front. I mean, it doesn't work anymore, because I'm always thinking. For the purpose of this lecture, I'm always thinking that particles are mostly jumping to the right. I mean, so I'm always thinking that I'm in a situation where P is larger than Q. Okay, so now you see that, I mean, they see this big block in front, and so it's not completely clear how they would react to this. Okay, so to figure out, I mean, we have to do a little computation, and so the idea is that no, I mean, this is not what's happening. I mean, rather, what the particles want to do, they just want to maintain this jump here. But, so I mean, this jump is called a shock. I mean, this is, I will say a few words later on, but I mean, let's just use this terminology. So that's a shock. So they're saying, okay, I mean, they're just moving to the right in this case, maintaining the shock, and they will move with a characteristic shock velocity, which I call Vs. Right? And now we have to figure out from the equation what the shock velocity is. And well, I mean, there's not so much in the game. I mean, the only thing which I have at my disposal is mass conservation. So let's do mass conservation. So we have Yes, now the area of this shaded region is rho plus minus rho minus. Okay, and well, this mass has to go somewhere, and so it might go to the right or it might go to the left. And so, if it would go to the left, sort of per unit time, I mean, then no, if it goes to the right per unit time, it will be according to the current. I mean, so, and the current is the one of the plus density, or it could go to the left. I mean, then I have to subtract this, and then it could go to the rho minus, right? And this is a famous condition that's called the Rankine. Can always Hugo, this goes back. It's 19th century. I mean, sort of when people studied this. Okay, so now let's do this for our particular case, for the RCEP. I mean, so you see that I can these are quadratic functions, and so I can figure out what the solution to these equations is, and what you find is that the Vs is nothing else but P minus Q. I mean, that sort of comes from these currents. I have to say over here, and when I sort of put this in the denominator, then because it's quadratic, I mean, this rho plus rho minus sort of cancels out, and the result is that it's 1 minus rho minus rho plus. Okay. And so you see that again, I have the possibility that this shock is actually moving to the right, or it's also moving to the left, right? Now, why are people fascinated by this? Well, okay, so the first point is that, so this is either sign. I mean, the first reason why people were fascinated by this thing is that here I imposed initially the shock, and then I just sort of determined through this equation how the shock is moving. Okay, I mean, that's fine. But the reason why people were very fascinated by it is that, they look at initial data which maybe are a little bit different than what I have. I mean, for instance, they would look at maybe something like this, some profile. Okay, I mean, this is Q, and this is my rho of Q at the initial time. And then you want to solve this equation, and now you have to understand the solution theory. And what came as a surprise, and what came as a surprise is that, even if I start with smooth initial data like this, you spontaneously generate the shock. This is also, usually, it's a rather, I mean, if you look at the equation, well, it's no longer here, but, I mean, your first intuition would be to say, well, it's a partial differential equation, and if I start with smooth initial data, they will say smooth. I mean, that's the first words which you are using, right? But people discover that that's simply not true, and you have to worry about, what kind of solution space, and you have to sort of understand, how these shocks actually appear. Okay. So this is sort of historically the reason why people were so much interested. So, at a later time, I mean, depending on this profile, of course, you have to sort of understand a little bit more about this equation in order to predict where it happens. But the way you should think about it is that maybe at some later time, I mean, there's sort of a shock appearing over here, right? Now, once it's formed, I mean, then we can stay. But if you wait long enough, then maybe because here it just will stay forever. But since we have a more complicated initial condition, it might sort of simply shrink and disappear and whatever, right? I mean, so. Okay, so this is one thing, but I mean, what I found more fascinating is the following. I mean, so let's see, I have to erase this here. Yes?
So if I take an initial condition where rho minus plus rho plus is 1, so that's a stable configuration.
If I go to the very extreme
No,
case.
I'm saying that rho minus plus rho plus is equal to 1. So then the shock velocity is 0 in that case.
Yeah, that could be. It's just standing still.
So
yeah.
then it just stays in
I mean, zero shock velocity is certainly not excluded, right? I mean,
okay.
Yeah.
So that's a stable. Then the step.
Also stable. Yeah. Okay. So why I was I fascinated is sort of I mean, after all, we're not studying, we sort of, in order to understand the microscopic dynamics, this hyperbolic conservation law is sort of very convenient. But of course, we also want to understand, what the particles are doing, right? And so, you see, what actually happens is that. So, okay, so here I have my shock. I mean, so. Maybe it's standing still, or maybe it's moving, but now the question is, what are really the particles doing? And you see, now there's a scale problem. You see, I mean, this is sort of on the macroscopic scale, right? And so, there are many, this means many sites. But now I want to look at so let me sort of indicate this like this. I mean, I want to look at sites, basically I want to, use my microscope and look on the scale where I see the individual particles jumping. And then you would say, I mean, it's clear that, this is something which I know, then there's a diffusive correction, and therefore, what I should see is something which sort of, looks like an error profile. Of course, this error profile, has a width which is sort of very small compared to on the macroscopic scale, but when I look on the lattice, I will see this smearing out. And that picture is totally wrong. And that, when I first learned about this, or when we studied this thing, this sort of was my motivation to go into a little bit deeper into this kind of subject, right? And so what actually happens is that is something different. And so, I don't have sort of a very good intuitive description, but the point is that apparently whenever a particle sort of tries to do that, this would mean that, I would have sort of compared to this one some excess number of particles which are sitting out here, right? I mean, that's what this curve says. And now, apparently, in this situation, the microscopic system sort of makes a very strong push, and it doesn't like to have this situation. It just pushes this particle towards the jump and the discontinuity. And rather than allowing for the smearing, I mean, they're pushed very strongly. And what is happening is actually that this jump is moving to another random location over here, and this is sort of essentially on the order of the lattice. And this is something which is true not only for this very specific model, but for real systems. I mean, for real fluids, when people study interface dynamics of fluids, I mean, let's say between plus and minus or things like that, between the high density and low density states, I mean, states where you have a stable interface, it's the same situation, that this interface is apparently sort of on the atomic scale. And here we have sort of a simple example where we can sort of see this sort of very explicitly, right? I mean, so the way you should think about it is that if I go configuration by configuration, so that's now sort of my empirical picture, is that, of course, there are fluctuations, but what I'm going to see is something which still has the shock, but it sort of deviates slightly from the exact shock velocity as predicted by the macroscopic by this macroscopic argument. Okay, and so the picture is the following: that so first of all, I can up to order 1, I can of course there could be a particle over here, and then I'm not totally sure whether the jump is at this location or maybe at some neighboring location. But the point is, since it's order 1, I can make sure that if it's sort of 10 steps apart, I mean, then I really know that this has moved by 10 steps, right? I mean, that level of precision I can say. And so the picture is that in fact what is happening is this shock is sort of itself making something like a random walk. And of course, if I start averaging, I mean, then of course I will see this kind of error profile, right? But for empirically, it's just sort of doing a random walk. Okay, and then there's another somewhat surprising thing is that now you might think, what is sort of the more microscopic picture of this thing, and then of course it's somehow quite clear, but it has one sort of amusing side point. I mean, so now I'm going to look at Q. I'm looking at space-time, and I'm plotting the macroscopic trajectory. I mean, so this would be the motion of my shock, right? And down here I had the initial condition. So here I have the rho plus, and you have the rho minus. Okay. And now you might think that I put a small perturbation here, and that of course will travel towards the shock. I mean, so this will go like this. They all because I'm linearizing around this one, they will all have the same velocity. It's the velocity which are determined by this linearized equation. And of course, on the other side, I have the opposite picture, and the condition that rho minus is less than rho plus. When you look at this sort of linearized sort of small perturbation, how they travel, I mean, they must be moving towards the shock. Otherwise, it would not stabilize. You see. If they are moving away, I mean, then we are in this picture over here. Okay, and so now you see what can happen is that I mean, on the macroscopic scale, a small perturbation will travel exactly with this velocity, and then it will come to this point, and then of course it has to be accommodated, and first of all, on average, producing this velocity, but on top of this, it's actually a random walk, a biased random walk, which has this velocity, and the actual position is sort of changing back and forth. Okay, and so now you could ask yourself, what is the diffusion coefficient of that jumping back and forth? And but what you can ask even more is that, this is also sort of an idealization. I mean, after all, it's stochastic. I mean, so perturbations are not really moving exactly on a strict line, but there's also some intrinsic randomness. So maybe this perturbation is also making a random walk, right? I mean, so now it becomes sort of like, you don't know which one is which, and then so how can you distinguish? But there's another randomness because the initial conditions are random. I mean, what one is dominating the effect? And this requires a little bit deeper analysis. But what you find out actually is that the next dominating term is simply the randomness in the initial conditions. So if by some sort of random event I have a slightly larger just an excess relative to the density rho plus, then it's this thing. Then I can assume that this is propagating deterministically, and the noise which I would pick up during this travel is sort of a subleading term, and that's something which you can sort of verify numerically. I mean, you just put, for instance, you can put deterministic initial conditions, which are just sort of like, if this would be density, I don't know, density 1/3, I mean, then you put 0, 0, 1, 0, 0, 1, 0, 0, 1, then you have sort of, then you have initial conditions which have no noise in them, but you still have the same macroscopic equation. And then you can verify that this will behave differently than if I put it down according to Bernoulli, right? I mean, so that's something which it's not just theory. I mean, as long as you are allowed to use a computer, I mean, you can sort of verify these things quite precisely. It was just sort of more the insight, I mean, which was important. Here was a question.
Yeah, so Herbert, so once the shock wave starts moving, the values of P plus and P minus, or rho plus and rho minus, they start to also change? Because we have the total number has to be conserved, right?
No, I don't understand. I mean, so yeah, I mean, particles, of course, move all the time, right? I mean, but no, but I mean,
but so if I maintain rho plus here, rho minus here,
yeah, no, I mean, so so what I'm trying to say, on the macroscopic scale, you just see, I mean, here maybe in this picture on the macroscopic scale, you see only this. If I amplify, you see that this sort of becomes it's sort of deformed to a biased random walk. So this rather than having this one, it really looks more a little bit like this, right? Okay. And then the question is, what is exactly the origin of that wiggling? Okay, and what I'm trying to say is that that's a deeper analysis. You find that it's actually it's a randomness from the initial condition which makes that particular wiggling. If I make the initial condition deterministic, so I've sort of by hand turned off the initial voice, the initial noise. I mean, then you will see a different behavior. I mean, it will still be random walk, but we will have different diffusion constants, right? I mean, we will have a diffusion which is linked to the noise which I pick up.
And do the boundary conditions matter? So here I was
well, okay. I mean, this is. I imagine that the boundary is very far away. Yeah, sure. I mean, if I do boundary, then okay, okay. I cannot put, in a ring, I cannot put two shocks, right? I mean, then one of them will be automatically doing this one, and so that's okay. And so I mean, just to write down one formula to amplify this is. What did I want to say? Yeah. Okay. So you can. You can actually compute. I mean, just for amusement. I mean, you can actually compute this. I mean, this diffusion coefficient. I mean, it's P minus Q, and I mean, just to tell you that when one can actually do some it depends on the height of the shock velocities, and then you find here rho minus times 1 minus rho. I mean, this is sort of indicating that it's somehow coming more from the fluctuations in the initial state. I mean, these are the fluctuations of the initial state, right? I mean, so then it's a rho plus times rho minus rho plus. Okay, it's not important, the formula. I just want to say that these things can be supported by computations, and then this is one of the results. Okay, so now I had told. No, I'm saying that, yeah, the diffusion constant of the location of the shock. I mean, so I'm saying the location of the shock is order 1. So, you know, at any moment I can sort of say more or less where the shock is. And then it's sort of like a random walk, and then you can sort of...
Right, but you said it has contributions from the initial, the fluctuations in
the
initial...
dominating contributions are from the initial noise.
Right, but if we ignore the, like if we have fixed initial conditions, then is there some surviving part still?
Yeah, I don't know whether we studied this in how detailed, but yeah, I believe there is some surviving. I mean,
There's still...
So you want to put here deterministic initial
Right,
conditions? Yeah. I mean, so you know, if I put here 1 1 silver 1 1 1 1 1 1 silver, let's say, and then here I put 1 silver silver, and here 1 silver silver, right? I mean, then you know, of course, the macroscopic picture will be totally unchanged. But the shock fluctuations will be different. I mean, but I forgot already whether we could sort of identify exactly what's happening then there, right? I mean, yeah. But certainly you will not. I think okay. I just don't remember whether we studied that specific detail. But one thing which we studied is the fact that you know when you do deterministic, then certainly you will not have anything like this. Okay, so now let's come to the diffusive correction. Well, I mean that's clear. I mean, so you know, I told you already yesterday. So we have this nonlinear current, and then you just do the density expansion, and so then you find there's a nonlinear diffusion coefficient. Well, sorry. Guess I want to write it like this here. So this is what we had, this is what we discussed yesterday, and then you might ask, you know, is there anything like Ring-Kubo formula? The answer is yes. I mean, there is a Ring-Kubo formula. I mean, it's slightly more complicated because I have to do correct subtractions, but you know, and this is something which you have to do for fluids also, because in fluids, you know, when you have momentum conservation, there will be always. You know, I mean, you always will have this term, and then in the Navier-Stokes there will be this correction. So anyway, I mean, this is a detail which I don't want to enter, but I just want to emphasize that you know, the formula which I wrote down for the diffusion coefficient as a time integral with proper subtractions of the carbon-carbon correlation, just as before, because you know we only use the conservation. Or there was at no point we use detailed balance. Okay, so we have this. Fine. All right. So you might now think, you know, let's do this, and then. You know, then of course, you know, if I add this term over here, then that means looking at longer times, and then you know, I will see this. Since I work here on average, I see this error function, etc. And now comes sort of was at the time sort of somewhat unexpected, is that when you look at this term, and when you look at this object, I mean, you find that this is actually equal to infinity. And so this means that, and this is special for one dimension. I mean, if I would do the same kind of things in 3 dimensions, you know, you would get sort of Navier-Stokes correction as you would do for ordinary fluids. But 1 dimension is very special, and in 1 dimension it so happens that this term is formally infinity, and therefore, you know, if I want to go to next order corrections, I have to be more careful, and there's a lot of interesting stuff going on. But, you know, this is too early. So tomorrow, you know, my lecture will be concentrating on what this means and what is sort of the correct description. Right? Okay, so on this part, are there any questions? Okay, so now let me come to the Landon-Lifshitz theory, which is an attempt to understand, you know, as I said already, it's an attempt to understand the fluctuations. And so this is a separate chapter. Let's see, how did I do this? Okay, so this is chapter 6. This is the non-equilibrium steady state. And what I'm doing is, maybe I alluded already sort of at the beginning, I put here particles, and I have sort of boundary, let me call it boundary chemical potentials, mu minus and mu plus. So here are the reservoirs. So in the bulk, I will assume detailed balance. So let's say nearest neighbor hopping, or I could be the SEP or any one of these detailed balanced lattice gases. But then I enforce this, at the boundary. I enforce a particular density, and it's easy how to do this. I mean, there's sort of let's say a C minus of eta. So this would be a rate which tells you how I see a transition from 0 to 1, and also how I see, the reverse, or how I see a transition from 1 to 0, right? And depending on how I choose the weights, I mean, this will sort of fix for me what is the boundary density, right? And then the same thing I do over here. So this will be C plus of eta, right? So this is now Glauber. It doesn't conserve mass because, I want to put mass or take mass out of the system. But inside, the bulk is perfectly mass conserving. Okay, so that's the setup what I want to do. And then okay, so if you do this sort of very naively, sort of the way you just put it like this, I mean, then what will be happening is actually that you have boundary jumps. I mean, so if I now sort of plot on a more larger scale, the density profile which I'm going to see, I mean, there will be some profile here in between. But then, if I don't do it in a specific way, I mean, then there's something which is called the boundary resistance. I mean, it just means that, the way how I put in and take out is sort of not matched to the system itself, right? I mean, and this, of course, is a very common phenomenon. I mean, so first there will be sort of a jump of, but it's really a finite jump, right? And the other one. And now, of course, in the level of a theory, I mean, you don't want to investigate the boundary jump. I mean, you want to investigate, what is the nest and what are the properties of the nest, right? I mean, then this is sort of an unpleasant sort of complication. And so the way how to do this is that you require that this weight and the, okay, so maybe I put it down here, C minus or plus detailed balance with respect to, well, I mean, obviously mu minus, or of course also mu plus, right? I mean, so what I mean is that, I have some underlying Hamiltonian with respect to which this is the detailed balance dynamics, and then I can simply, add the chemical potential and take flip weights which satisfy detailed balance. But then now in this boundary there will be two different parameters appearing, either the mu plus and mu minus, and therefore I sort of avoid having these kind of boundary jumps. I mean, what that if I make so in this case, I mean, if I make mu plus equal to mu minus, then of course there's a unique steady state because I'm pumping in particles from the outside and the inside. So this is sort of the one with respect to I have chemical, which I have detailed balance, and then there's of course the mu plus and minus of n, right? I mean, there's a unique steady state, and the one which we know already. I mean, so this is not so interesting. But now, of course, for the nest, I want to make mu plus different from mu minus. I mean, then there's a nest. I mean, it's unique because you can sort of, through these boundary jumps, I mean, you can reach any configuration from any other configuration. Well, the question is, what are its properties? Okay, and of course, that's not such a simple question. And even if you start, making simplification, maybe if I put here the RCEP or the TARCEP, even then it's a highly non-trivial question. But I mean, for the RCEP and TARCEP, people have developed tools. I mean, there's something called the matrix product ansatz, which was invented by Derrida, and which allows you, Bernard Derrida, which sort of allows you to say, quite a bit more about the nest than what I'm going to do, right? But I mean, this works only in very special cases, and if you go beyond these exactly solvable cases, then It's sort of like a completely white area, and so we really don't know. Anyway, so I still want to ask the question, and so okay, so in particular, what I would like to know is of the most natural question. Okay, so maybe I should first introduce one notation. I mean, so in the NES, you will have some average density. I mean, this is now the NES average, which I call Vs of X, I guess, or then later on we will use continuum, then we'll with the Vs of Q. And but the question which I'm asking really is a statistical mechanics question. I'm asking, you know, what about this pair correlation, and then we somehow know that maybe it's natural to subtract the average. And of course, you know, there's no translation invariance anymore. I mean, you know, it's sort of the density itself is changing, and you know, there's no reason why if I shift these 2 points somewhere else, I mean, of course, you know, it will not be the same. I mean, so all these nice properties which you have for spatially homogeneous systems, they are of course lost. But nevertheless, I would like to know something about this thing. Okay. And so now the question is, what do I do? And as I said, I mean, there's this Pullman method, I mean, which is called the Landon-Lifshitz theory. And the reason why I want to explain this to you is that, you know, of course, Landon-Lifshitz didn't think about lattice gases, but the point is that you know, beyond this deterministic hydrodynamic, there's sort of a natural fluctuation level, and from this fluctuation level, you can also learn a lot of things, right? I mean, and you know, it's sort of what people call Gaussian fluctuations. It's sort of more like, you know, law of large numbers is the exact equation. I mean, you know, the macroscopic equation, and then relative to this, and you will have fluctuations which in many systems are simply Gaussian fluctuations, and understanding these fluctuations tells you a lot about the statistical properties of system. Now, of course, you know, they are again related to having, you know, you want to have a central limit theorem, so this means that, you know, I have to look at regions where I have many particles, or, you know, you know, people have studied also these systems which are also interesting for other purposes, for very short systems, right? I mean, you know, you just take the 10 latticide, and then you want to know what's happening. That's of course a totally different ballgame, right? I'm looking here at the very large system and want to understand that, right? Okay, and so now the question is how to do that, and no, okay, so that will be okay. In order to do this, I have to sort of remind you of a little bit of this type of you know, the mathematical structure which is behind this fluctuation theory, and so this is more like, you just think of this like an insert here. So you know, now I'm on a scale, you know, which is large to the lattice scale, but I still want to study fluctuations, okay? And so I have fluctuations. And now I see that, let's see, yeah, okay. Okay, so I guess I changed slightly my notation anyway, so you can follow. I mean, so fluctuations, and let me just, you see, I mean, in this system, well, eventually, you know, I want to do the steady state, but you know, to find out the steady state, you know, it's sort of still a dynamical problem. So a priori, these fluctuations are somehow in space and time, right? And the fluctuation theory is always formulated as a space-time theory. So I have some fluctuating function, which in our case depends on x and t. And so I'm sorry for this sort of oversight. I mean, you know, I use x here, and then so, okay, I should have, okay, so I should have labeled this sort of as j, right? And so maybe here I should have used eta I and eta j and eta I, eta j. Anyway, so now for this insert, I mean, x will be a continuum variable. I mean, so, and since my problem is one-dimensional, the space will be one-dimensional, time, of course, also. And now, you know, the fluctuation theory have a very canonical structure. I mean, so you want to look at the time evolution of these fluctuation fields. Of course, the concrete system will come when I specify the operators, but at that moment, I mean, it's quite general. And so it's a Gaussian fluctuation theory. So basically, what you want to have is that if I start with Gaussians, I mean, they will stay Gaussians. And that happens only if this equation happens to be linear in phi. And so, so the first thing I'm writing down is a phi of x of t. So that's a drift term. But I'm a function, and the a is an operator, but the a does not act on t. So it's acting just on the x variable. So in our case, I mean, the a would be like a second derivative, for instance, but it could be some more complicated operator. I don't want to specify this at the moment, but the point is that it does not depend on time. It does not act on time. It just acts on the x variable. Okay. All right, so that's one thing, and then I mean, I want to have some decay, and so maybe I mean, here I put the plus sign, so in fact it should be negative, but a is not, so a could be also, so maybe I should have put this, and could be also this operator, right? I mean, I don't want to a priori assume that it has any kind of self sort of symmetricity or something like that. And so, but that's to remember that I want to have something which is actually decaying. I mean, I want to assume that this is sort of, in some sense, sort of less or equal to 0, right? So I just want to make sure that when I take the exponential, then things are sort of contracting. Otherwise, I will not have any stationary measure at all. Okay, and then, but that's not all. I mean, that's just a deterministic equation. You see, this is sort of one of these linearized equations which I talked about before. But then there will be noise. I mean, so then I put here, I put here a plus, and then I put here a noise term. That's xi of x and t. And now the xi is something which of x and t, which is white noise. Gaussian white noise, so these are all Gaussian random variables, and when I look at the mean, I mean that's just 0, and when I look at the covariance, then it's delta correlated in x and t. I'm not writing down the formula. I mean, I mean, if I specify Gaussians, I mean then the mean and the variance suffices, and this variance is sort of delta correlated in x, and maybe I should write down this. Okay, delta correlated just means that it's delta of x minus x prime, and it's delta of t minus t prime. Okay, so but now you see just adding noise is totally naive. I mean, for instance, in these kind of problems, we have a conservation law, and so if I just add xi here, then would automatically say violate the conservation law. So this is too naive, and so also the white noise has to be modified a little bit, but again only in a spatial way. And so I call this B, and B is again sort of a linear operator. I mean, so as I said, I mean one example for A and B would be for instance just first order derivative. But it could do in principle something more difficult. But I just want to emphasize that what I'm talking about here is sort of a general scheme which can be always applied, and then what A and B is sort of depends on the thing. Yes.
So now you're looking at multiple conserved quantities, because A is a matrix.
No, I mean because I'm looking at the scalar field. I mean, it's sort of I mean when. No, A is an operator acting on X, so it's a matrix if you want, so right. I mean, but it's really, A is okay. So in my case, okay, so maybe I should say this. I mean, in my case, well, it will be slightly more complicated, but anyway, in my case, the B will be something like this, and the A will be something like the X squared, right? Okay. Okay. Okay, just and here it's the same idea. I mean, the B is independent of time. It just acts on X. You will see in a second, I mean, which way this comes. But the point is that the operators which will appear in this non-equilibrium steady state are a little bit more complicated than just these operators, right? I mean, and the reason why they're more complicated is that you see, I mean, you know, in the steady state, I have some profile, and so all the terms which are appearing, you know, I mean, the noise strength and then also the decay strength will depend on where I sit, and so I get some spatial dependence. Okay, fair enough?
So they could be just first derivative also.
Well, in general, yes, could be also first derivative. I mean, you know, at the moment, I don't want to be too specific, right? Because I just want to have sort of two key formulas which I want to I mean, I don't know, not remind you, but okay. And then of course, then of course there is there's a steady state which I have to sort of explain to you in a second, right? I mean, so an S if you want so. I mean, there's no reversibility in this, which is sort of this sort of equation, right? So there's a steady state, and a priori I don't know what it is, but of course, you know, it's a long time limit, so it's again a Gaussian probability measure, and it's specified by its covariance. I mean, so now I leave out the x because I'm looking, so to speak, at infinity or at some, let's say, at time t equals 0, in order just to define what I mean by the steady state. I mean, so here I have a phi of x, average is 0, and then there will be covariance, phi of x prime. And you know, at the moment I don't know what it is. I mean, but you know, I want to give it a symbol. I mean, so this is now, if you want to sort of an integral kernel, right? I mean, it's just a matrix with indices x and x prime, but they are in R, right? Okay, so now you do some simple computation, but which I will not do because, you know, would again sort of deviate from the main topic. But so there are two general facts. So the first thing is that the minus A C plus C A transpose. So I write transpose because, you know, these are all real operators. Is equal to B times B transpose. So this is the solution to this thing, because it's Gaussian. I can do the computation, and you know, of course, since I write down the equation, I assume that A and B is known. And then I can get an equation for C, and that's the equation for C.
How do you get that equation?
How do I get this equation? Well, I mean, you know, basically the way I do it is that you know, since the linear equation, I can write down the solution, right? It's e to the at acting on initial condition, and then also e to the at acting on the noise, right? I mean, and then I just compute what is the covariance of that state at time t. And then I'll take the long time limit, and then because I have this decay assumption, you will see that, you know, this converges nicely, and it's this result which comes out. Okay. I mean, it takes you a little while to do it, but I want to, you know, when you look at this formula, you say, oh, it's very nice, but you know, I still have a complicated operator thing, and so I don't really know how to solve it, right? And so let me just sort of, then you can ask the question. I mean, so let me just say that I can solve this equation, and presumably, you know, maybe if I do the argument which I indicated to you, I mean, you get directly the solution in the way which I'm going to write down, but very often this form is sort of more convenient. So actually there's a formula for C. That's the integral from 0 up to infinity. Yeah, it's this formula which comes out when I write down the solution. Just take the long time limit, right? I mean, because you see, no, okay. So you want to know? Okay, so let me do this a little bit, just in one moment, so that you can sort of understand that that's not really a miracle. I mean, so if I write down phi of x of t, I mean, this will be e to the a t times the initial condition, right? But then I have to add the noise. It's 0 up to t, and then it's ds, and then I have here my b times xi of x and s, and then I have still to propagate according to e to the T minus S. So this is the solution to this equation, right? And now I compute the covariance, and this term sort of goes out because, you know, eventually sort of the initial condition will be forgotten. I have sort of some assumption which sort of guarantees this. And then you know, if I do the covariance here, I get these delta functions, and then I have to plug it in, and then you get the formula which I'm going to write down for you in a second. Okay, so this is dt. It's e to the at. Okay, so I hope this is correct. Yeah. Yes, okay, so this is the thing, okay. And now you can verify, you see, if I insert this, I mean, with this minus sign, if I insert the b of t, I mean, if I insert it over here, then you see that eventually I can put the derivative in front of the whole term, and then, you know, it's an integral over derivative, and its value is at 0. This is why I have the minus sign, and then you get the correct thing. So this is already the end of the insert, okay? Okay, so now how are we going to apply this to our problem? Okay, so I first have to figure out what are these operators, right? But you see, we know to some extent. So what is the idea? The idea is that, you know, these fluctuations are sort of something which is, you know, which, I mean, you know, sort of, they're local in space and time. And so the first thing what I should do is, as an exercise, understand what would be the fluctuation theory in the homogeneous case. So first I do the homogeneous case. Okay, so this means that I'm not looking at the steady state. I'm just looking at the situation where, you know, everything is just uniform. It's basically equilibrium because I assume detailed balance. And so what you find in this case is that so, you know, I mean, in the bulk I will have a diffusion equation. So you will find for the A will be I mean the d of rho. And let's see, I have to make sure that I'm doing this correctly. Yeah, so, no, sorry. I mean, so, okay, there's some question where you put the derivatives, and I can go into it. I mean, you know, here, this is still constant. I mean, so, you know, rho is the background density. I mean, then, of course, I can put it anywhere. But for the actual you know, for the actual non-equilibrium steady state, I have to be a little bit more careful. So this will be the A. I mean, that's just saying that you know, it's just sort of linearized around thermal equilibrium, right? And then for the D, I mean, we found out already that well, how much did we find out that? Well, okay, maybe not so much. Okay, anyway, so let me maybe talk about, okay, so yeah, for the B, now I can see that I'm writing down this formula, and maybe I don't really justify this so much. Anyway, so let me just tell you what the B will be in our case. I mean, so the B is, I put a minus sign. I mean, this is sort of unimportant, but when you do this linearization correctly, I mean, then you find out that it's 2 chi times d times the dx. And this, you know, you have this Einstein relation you can write as minus 2 sigma dx. So I see that, you know, in my notes I didn't put any more details because I think, okay, let me just sort of say that this is what comes out if you do the fluctuation theory. You see, I'm doing here fluctuation theory in thermal equilibrium, and so I know somehow what all these objects are. And okay, maybe I can actually, I can actually I have a good argument to tell you. Okay, you see, since we are in equilibrium, of course I know already I know already the steady state. I mean, that's just my equilibrium state, right? And so you see that in equilibrium, the C operator you know, in equilibrium, I know that my correlations are sort of decaying very quickly. And so since I'm looking on the large scale, it looks like a delta function. However, I have to tell you what is the strength of the delta function. Now, the strength of the delta function is exactly the susceptibility. So this is nothing else but the chi. Oh, yeah, this is what I wanted to say. And then there's the delta of x minus x prime, right? And the chi, remember that you know, it's just sort of, you know, what would be the corresponding microscopic object. I mean, you know, I just have to sum over all j, and then, you know, I do the equilibrium average eta 0. And it's just the same thing what we had all the time, right? I mean, so. Okay, yes. No, at the moment I'm looking at equilibrium because I was basically, the philosophy is that I want to look at the little piece over here, and then I'm just sort of studying what is the equilibrium.
No, like the operator A, when you wrote the D is inside the derivative.
This one, yeah.
Yeah.
At the moment, you know, this is just a number.
This is just a
So
constant.
I could have put it anywhere, right? And okay, so now I can tell you where the B comes from. I just sort of forgotten in my notes. I mean, so you see that I'm now I'm in the situation that I know A and I know C, and therefore I can determine B, right? And if you do this thing, and then this is sort of the result, and you know, it's a little computation. I mean, with these formulas, but you know, I can just plug it in here. You see, the A is the second derivative, the C is a unit operator, but with this chi, and then, you know, the B must be second derivative. So then the B must be first derivative, and the coefficient which appears in front of the B is exactly this one. And then I use the Einstein relation, so that's the correct formula. Yeah, okay, so now I've just forgotten that I actually wanted to say this argument. Okay, so now what is A and B? But now we come to the NES. And so now, of course, life is getting a little bit more difficult, but still, I mean, it's okay. So we have dt of phi plus dx. Okay, so now I have to write the A, and you know, this is why I voted like this. Okay, so there's a minus sign because it's a diffusion. And then the D, if you do just sort of think about this for a while, I mean, then the D actually appears on this side. But now you see the D is a function of the NES density. That's this density here. And then, I mean, you know, I'm using now a slightly poor notation, but you know, this is a function of x here. So okay, so this coordinate has become an x in my notation now. So you see that I get a second derivative, but with a diffusion coefficient which depends on where I am. And so this makes this operator, of course, a little bit more difficult, because, I mean, this is sort of a multiplication operator here. I have a second derivative, and so I cannot so easily deal with these operators, right? But still, I mean, you know, I can sort of formulate the problem. I see questions, but let me first write it out. I mean, so then I have the noise. I mean, so there is the ddx. I mean, this I put in front. So there's a conservation law, and then I have the 2 sigma of x. You know, the chi depends on x. The d depends, of course, also the conductivity depends on x, and then I have here the white noise. So this is my Landau-Lifshitz equation for the non-equilibrium steady state. So let me just repeat. I mean, so I have noise, but the noise strength depends on where I am in the steady state, and the strength of the noise is simply the conductivity. The phi. I had forgotten the phi. The phi must be here. Yes. Thank you. That's very good. Exactly. Yes.
So why not these Yeah, but no, the D, why is not outside the second derivative?
Why? Well, this is what I said. It's a little tricky argument. I mean, which I don't want to sort of. Yeah, I mean, at the moment, I mean, you might be worried. Of course, I mean, you don't want to put it outside here, right?
Just
I mean,
but
you could have interchanged these two things. Yeah, that's sort of okay. You have to think a little bit why this is exactly like this. Yeah.
Because if I think of this like a current, then
No, I mean it's a different operator, right? I mean if I put it out here, I mean then you get the commutator, and so no. But I'm saying that if you sort of think about this slightly more carefully than what I do here at the blackboard, I mean then you find that the D has to really stand like this, right? It's related to the way how you discretize. Not how you discretize, how you linearize your equation and so on. Okay, so now I think I have written this correctly. So here this is 0, and there are these two terms. I mean, one is sort of the decaying term, which is this one, and the other one is the B term, which is a first derivative. This is sitting outside, but then there's sort of a strength term which depends. Okay. And you see now I'm basically finished, right? I mean, well, I'm not finished, but. Let me see, I have to look on my watch how much time I have. Okay, so I have very little time. Okay, so that's fine. I would like to finish this because, it's not so good to take it up next time. Why am I, in a sense, finished? I mean, you see, what I was asking was, yes?
In this term, would there be root over sigma, the noise term?
The square root, yeah, very careful, very good, yes, absolutely right. No, it has to be the square root, yeah. Yes. Yeah, it's also here in my notes, it's the square root. Okay, so now I want to compute the steady state, so I'm using this formula here, right? But now you see I have a difficulty because the A and the AT are not such simple operators, right? And also, well, the B term is sitting down here. This is maybe not such a big deal, but still, I mean, you see that to go, writing down the formula is okay, but then actually manipulating the formula is not okay, right? And so I will spare you. I mean, these are details which maybe are of not too much interest here, and so I just want to jump ahead and want to tell you what the result is. So the way how you do it is, you would think that, okay, so the way how you do it is that you write your CX prime, and now you see, I mean, the naive guess would be that what I'm going to see locally in the steady state is simply, the same type of covariance which I have in my equilibrium, which is the one which is sitting up here. That's just saying that, locally it really looks like an equilibrium state, and that's it. Okay, but it's clear that this is sort of has to be tested, and so one way to do it is to say, I have a local equilibrium state, which strength has psi, which of course depends now through the Ness on x. And then I have here delta of x minus x prime. So this is, so to speak, the local equilibrium contribution to this correlator. Yeah, because this would be the first, naive guess. Okay, but then presumably there's a correction. And since we have an exact formula, I mean, on the level of this Landon-Lifshitz, I can just sort of investigate what the correction is, and then so I take the non-equilibrium correction of x and x prime. Okay, and so now comes things which you have to put it in, and okay, anyway. So I'm not going into this. I mean, there are lots of interesting details, but I mean certainly not interesting for this audience here. And let me just sort of do there's the one simple case where you can get very explicit solutions, and but the result which I'm displaying is sort of quite generic, and you will see in a second. So it's clear that if I do the simple case would be the SEP as bulk, because then the D is just then D is actually independent of x. I mean then this term is particularly simple, but I still have an x dependent sitting over here. And so let me just give you the answer and discuss the answer. So I mean the result, I mean in the case of the SEP, I mean so this is the symmetric simplest case, is x prime, and It's actually minus delta of x to the minus 2 with Dirichlet boundary condition. So Dirichlet boundary condition means that the field, has to vanish at the two boundaries, 0 and 1. Okay, and this is sort of an inverse of an operator, so you can sort of. Okay, so let me write it like this. I mean, the C operator is given by this. Okay, and but this inverse you can figure out in our particular case. I mean, so I can write for you now more explicitly what's the non-equilibrium contribution. Of course, you have the local equilibrium distribution, but then you have a correction. And since you can explicitly invert this operator, it's 1 minus x prime times x. So I'm now on the interval 0, 1. This is for 0 less than x prime. And then for the other one, I mean, you get a similar type of expression, 1 minus x. And this is for 0 less than x prime less than x. Okay, and okay, and then this has to be multiplied with the gradient square, so to speak. I mean, so this is rho plus minus rho minus squared, right? I mean, so. Okay, so. Okay, so first I want to point out, this simple factor. I mean, so this means that if I have small driving, I mean small difference in density and boundary densities, I mean then this will become small. I mean, so that's sort of already a good sign. But now you look at this thing, and you see this means that this is a function which lives everywhere, right? I mean, if I compute, for instance, another simply self-correlation, I compute the Cn of xx, then you see, it's 1 minus x times x. I mean, it goes anywhere. I mean, at the boundary, I mean, the fields cannot fluctuate because this is where the reservoir is. But otherwise, inside they can fluctuate. And the point is that you have long range correlations in your steady state. You see, it's not that you might have hoped that. You might have hoped that you get something which is sort of localized, but you see x and 1 minus x. I remember that this was our. You see, this means that this occupation and this occupation are still correlated. When you put in sort of numbers, you see that actually the prefactors and things like this. These are actually I should really say weak long-range correlations. But this is sort of a generic factor, and the reason why, one way to understand this is that, by particular symmetry conditions, if you are in thermal equilibrium, these fluctuations cancel out, and then eventually you see only the exponential decay. But if you have a conservation law, and if you induce some spatial variation, then through the spatial variation, you have to sum up all these correlations, and they simply don't cancel. And at the end of the day, they sort of combine into something which is actually no longer short range. Okay? Now, if you do this in 3 dimensions, it's again the inverse of the Laplacian. So this was 1-dimensional, but if you do the same discussion in 3D, then you see that you get sort of this Coulombic type of long-range interactions. And then you might wonder whether this is just fantasy or whether you can actually see it. And the answer is that yes. I mean, there are experiments which have been done, some time ago. So of course, not on the SEP, but on real fluids. And what you do is the following. I mean, you take a fluid, and so now you want to sort of induce a non-equilibrium steady state. And one natural way to do this is you take a fluid and you heat it from above and you cool it from below. So there's no instability, right? I mean, but nevertheless, I mean, there's energy flowing through the system, and then there will be a gradient there will be transport, and there will be gradients in the density, right? I mean, because you know, it's heated on one side, but you don't get any Bernard instabilities. Okay, so this is what you do, and then you know you apply exactly the theory. It's sort of, you know, somewhat more sophisticated, but essentially a theory of this type, and then you do light scattering. Light scattering sort of measures for you exactly this density correlation, and you know, you have to do it at very small angles, so the experiment is not totally easy, but you know, it has been done, and you know, you see exactly what is predicted by the corresponding Landon-Lifshitz theory for the three-dimensional system, and you know, with all the extra difficulties that we have more conserved quantities, etc., right? I mean, so it's a more longer enterprise. I mean, you know, it took a while. I mean, there were sort of, you know, a whole sequence of theoretical investigations. You know, at the beginning was sort of, you know, extremely complicated what people did, and then at some point people realized that, look, I mean, if we do this fairly simple-minded Landon-Lifshitz theory, we can sort of bypass all this complicated, so more microscopic type of computations, and we will predict the correct result, and yeah, it is confirmed. And there's another area where this comes up is, I just want to mention the name. I mean, there's this notion of long-time tails, which is a similar type of thing, but it somehow sort of, you know, the same origin, and it can be very easily explained once you do this Landon-Lifshitz fluctuation theory. Okay, so I stop here over time this time. Thank you very much.
Okay, thank you. All right, so today, before we go on to today's talk, I just wanted to finish off what we were just about to discuss, but you know, like lunch intervened. So we'll quickly finish this and then go on to the content of today's lecture. All right, so just to give you a reminder, so we were looking at this experiment of Milgram, in which he essentially got several people in Omaha, in Midwestern United States, to basically hand deliver packages to their known acquaintances such that it reaches a designated person in the city of Sharon in Massachusetts. Okay, and then we found that there were some paths through which some of these packages eventually reached the stockbroker, and then Milgram basically looked at all the packages which had eventually reached their destination, found out how many hands it changed, and then said that the average was slightly greater than 5, and you know, you get this 6 degrees of separation number as a result. And you know, you can do a back of the envelope calculation to kind of satisfy yourself that, yeah, I mean, that's about the correct number if the population of this planet is kind of connected in a random network. Okay, so you know, if you say that you know roughly 100 people, and let's say the population of the planet is let's say 10 billion, so you know, about 10 to the power 10. So then what will be the average path length? So that would be log 10 to the power 10 by log 100, right? And so basically it would be 10 by, yeah? So then you get 5. Okay, so 5, you know, it's around what Milgram got. Okay, so you'd say, okay, everything hunky-dory, but you know, the big problem, of course, is that social networks are not random. You know, as one of you mentioned yesterday, that you know, if I know 100 people, then each of those 100 people will themselves know, you know, again on average 100 people, but that doesn't mean like, you know, I have what 100 times 100 would be 10,000, right? that I have 10,000 friends of friends, because many of the friends of my friends are also my own friends, because social networks tend to be highly clustered. Okay? So the big question was, how come, despite the fact that this argument shouldn't work in social networks, because social networks are not random, despite that, using this back of the envelope calculation, assuming random networks turns out to be pretty similar to the kind of average path length you see in social networks. So this was a big puzzle. Okay? And in '98, a paper came out in Nature, which is kind of what we consider to be the year in which the big interest in complex networks really hit physics. And this paper is, pretty much responsible for that. I would encourage all of you to actually take a look at this paper. It's highly readable. Actually, all of Steve Strogatz's papers are highly readable. I mean, he has this gift of, making even the most complex things highly understandable. So this was a paper written with his then graduate student Duncan Watts. And Duncan Watts also has a brilliant writing style. As I mentioned in the first lecture, that he has this popular book called 6 Degrees, which is highly readable. And I recommend, if any of you are planning to get into complex networks, do try to get hold of a copy of 6 Degrees and read it. It's like a, it's almost bedtime reading. I mean, it's very lucid, has almost no equations and so on. Nevertheless, you get a lot of insights about networks and how to approach them using that book. Strogatz also has a book on networks, but it's more on dynamics on networks. So basically, his book is called Sync, and he's basically talking about synchronization. Okay, and he does talk about networks, but in the context of how networks help things synchronize. All right, so what was this paper about? So it's effectively, I think, just a 2-page paper. And, they say that the really, important papers are those which, after reading, you think, why didn't anyone before them think about this? The idea is so simple and elegant, anybody could have thought about it, but it turns out that nobody simply had that, leap of thought that, maybe we can do it this way. Okay? So this is how they approached this. So they said that, the history of this, how they actually came up with this is very interesting, and Duncan Watts actually talks about in his book how they came up with this idea. That itself is a fascinating story. I won't go into that for lack of time. But effectively, the idea was that, look, on one end, you have regular networks like lattices, which physicists study. At the other end, you have random networks, which mathematicians study. And there's almost no conversation between these two groups. Okay? So is there some way that you can have an interpolation technique by which you can go from regular networks to random networks or back? So one very simple way in which you can do this is the following. So you say that, okay, I'll take a regular network, and with a probability P, I will take each of its links, cut it, and then randomly rewire it with, any other node in the network. So for example, here I have taken this link and basically taken the, the two vertices that this link connects. They are now connected. So this one is connected to this one, and this one is connected to this one. Okay? And then you take this link over here. Again, you cut it, and then this one you connect to this one, and this one you connect to this one, okay? And so on. So what fraction of the existing links of the network are, in this way randomly rewired completely depends on this probability P. Okay, so you can also think of P as the fraction of the random long-range connections that are there in the network. Okay, so so the way they did it basically ensures that the total number of links in the network doesn't change. Okay. So if you keep doing this, eventually you would be taking each and every one of the links in the network. So if p equal to 1, that means with probability 1, I mean with certainty, you will take each of the existing links in the original regular network and then randomly rewire it. Right? Of course, even if you randomly rewire it, sometimes just by chance, you will actually connect neighboring nodes. So, there would be some links which will still be there between neighboring nodes. Okay? But effectively, that's just like a random network, because you are taking each pair of nodes and with a probability p, putting a link between them. All right? So p is now a continually varying parameter by changing which you can go from a regular network to a random network. Okay? Yeah.
Just to be sure, you are preserving the number of links, right?
Yeah, yeah.
So when you replace that bottom one, so you remove that.
Yeah.
And then take one of the two vertices and then connect it to some random guy, not both vertices, right? Here it looked like you connect.
Oh, yeah. Sorry, this picture is slightly wrong. Yeah.
You just connect.
Absolutely right. Absolutely right. Yeah. So thanks for pointing it out. Yeah, when I had made this picture, I had actually completely forgotten about this, and so but there's another. It turns out, but good that you raised this, because it turns out that doing analytical calculation with this particular version of small world network is quite difficult. So there's another variation where they keep the original regular network and just keep adding long range connections, okay, which is analytically much more tractable. Okay. So there are both variations existing in the literature. Okay. One where the links are preserved, another where you still keep the original regular network backbone and then just keep adding random long range shortcuts. So you ask, okay, how many random long range shortcuts do I have to put before it starts behaving like a random network? Okay. Now, if you look at these two extremes, these are both well studied. So I mentioned that regular networks have path lengths which are basically scaling as n to the power 1 by the spatial dimension. Okay, so then the clustering is very high. So you notice that many of your neighbors. So if you look at this node, it has 8 neighbors, and many of them are also mutual neighbors. So for example, if you look, let's focus on this one. So these two neighbors of this node are also mutual neighbors. Okay, so the clustering is also pretty high. And then the degree distribution would be delta function, because each of them would have 8, degree of 8 and so on, except for the edges, of course. Okay? But we can take care of that by taking periodic boundary condition or whatever. Okay, now if you come over here, we know here the path length would scale as log of n. The clustering should effectively be lower than that of regular network, and the degree distribution should also be different. And so the question was, okay, so as you go from here to here, what happens to, for example, path length and clustering coefficient? How does it change? So we know that path length should be high here, low here, and clustering should be high here and low here. So now the question is, okay, does it change like this? So as you vary p and you look at path length, so we know that it should go from high to low. So does it go like this? And then if you look at clustering, again we know it should go from high to low. So using some other axis, I mean the values are of course not the same for the two, but suppose you scale the axis such that you can draw both these curves on the same graph, does it also follow like this? Okay, yeah. Sorry? The y-axis, yeah. So I'm using the same axis to plot two different things. Okay, so the yellow curve stands for path length, and the, what color do you call it, pink, is the clustering. Okay, but the axis values are completely different. Okay, because they are of course not measured using the same unit, so to say. Okay, so I'm just drawing this just to show that, you know, do you expect the nature of the two things to be similar, and should both be decreasing in this kind of a smooth linear fashion? Okay, or what way should it change? Okay, that's the question. Yeah. Okay, so here long range simply means that you are choosing the pair of vertices usually connected purely at random. Okay, so that means it could be from any point of the network to any other point in the network. I mean, here the problem is that when you say long range, it brings to your mind some kind of a, you know, spatial metric and so on. But long range was simply supposed to mean that in principle it could be connecting two nodes which are anywhere in the network, unlike in the spatial regular grid where always you are looking at nearest neighbors. Okay, now strictly speaking, regular networks will be defined in some spatial dimension. Okay, because you have to define like who's your physical neighbor and so on, whereas random network has no such restriction. Okay, there is no underlying spatial dimensionality in which you'll be embedding it, right? So that is one of the, you know, objections which were made, that somehow Watson-Strogatz' version assumed that you start from, you know, some spatial dimensionality, and then basically you go to, you know, something which is pretty abstract and so on. And you know, the reason they called it long range was precisely because they started from something which was embedded in some spatial dimension. So if you do have an underlying spatial dimension, then you can actually define a metric, right? But the whole idea of random graphs is that metric has no concept there. In topology, you know, metric almost doesn't matter, right? So, so what does it mean to say long range in random network? You have to interpret it a bit loosely. You have to say that, look, any two pair of nodes can be connected. There is no restriction on them. Okay. Okay. Now, what did they see? So you expect high clustering, large path length in this end, low clustering, short path length here. What about here, where P is between 0 and 1? Okay. So you might say, okay, it would be some kind of a medium clustering, medium path length maybe, okay, if you believe this. Much to their surprise, they found that it has high clustering exactly like the regular network, but short path length exactly like the random network. Okay. Now, of course, this is not a very quantitative statement, right? So you would like to see how actually this changes with P. So that is what they did. So here you are plotting P along your horizontal axis, and along the vertical axis you are plotting scaled values of clustering and scaled values of path length. So that's why you can actually use exactly the same thing, because even though the actual value of clustering numerically will be very different from the actual value of the path length, because you are expressing it with respect to the maximal clustering and the maximal path length, they will both be a number between 0 to 1. Okay. Is that clear? Okay. So what they found was actually very surprising. So they found that indeed both quantities decreased from 1 to 0. So what is this C0 or NL0? So this is the clustering coefficient for a regular graph, and this is the path length for a regular graph. Remember, both of these are supposed to be maximum in the sense that for a regular graph, the clustering is high and the path length is high compared to if you put in such random long range connections. So if you express everything relative to this C0 and L0, you know that things can go only decrease. Okay? So that is something that was expected. But what they didn't expect was the following. The fact that as you vary P, the average path length drastically starts falling the moment P becomes greater than 0. Whereas clustering almost doesn't change until at very high values of P, so that the local property of the network essentially retains this regular character until you have a huge number of long range shortcuts in the network. So by this point only you can disrupt the local character. But the global character of the network starts changing immediately after you introduce just a few. When n tends to infinity, you can say that as soon as P goes to 0 plus, your average path length would start decreasing drastically to almost the value that you expect for P equal to 1. And this is precisely why the random network argument of 5 or 6 degrees of separation, whatever, actually works for real social networks. So our real social networks tend to be highly clustered, but we do tend to have very few connections which would be outside our immediate social clustering. Okay? And it's those, what do you call, long range need not be geographic. I mean, I don't necessarily mean that, when I talk about a long range connection, that this connection you have with someone, let's say in the US or Australia. Long range could be in terms of that person is not known to any of your immediate circle of friends. Okay? That's what I mean by, long range shortcut. It's outside your immediate social cluster. Okay? And it's through these long range shortcuts that you actually can very rapidly connect to any other person on this planet. Okay? To turn a network's global behavior into that of a random network, you actually don't need to make it fully random. All you need is just a few long range connections. Okay? So that was this big revelation of Watson-Strogans. Okay? So you can say that this entire region where your local property is that of a regular graph, but your global property is that of a random network, essentially constitutes the small world of small world networks. Okay? Yeah. Yeah. So this becomes sharper. So this LP by L naught curve essentially becomes sharper and sharper and sharper. So that's why I said that as soon as P goes to 0 plus, you will have the property of a random network. Yeah.
Two PC.
Sorry?
There are two PC. One is from CP and one is from LP. In the n tends to infinity.
Okay. So people usually don't talk about this in terms of PC because they're more interested in how the path length properties increase, because for local properties you don't care too much about like how does the local property change and so on.
Okay. There's no PC. It's almost at 0.
Yeah. So it's 0 exactly. So that was actually the a very embarrassing episode in network science. So I think what was I don't want to name the wrong person, but someone who's now a very famous network scientist actually managed to publish a PRL where from numerics he claimed that PC was finite. And so it was the only PRL I know where in the same issue where the paper has come out, there's also a rebuttal by two groups of people who show that this is wrong. So these guys actually, after it got accepted into PRL, put it in archive. And the moment they put in archive, other people kind of showed that there was you can analytically show that PC is actually 0. Okay? And so, but I think for whatever reason PRL didn't want to retract that paper. So they decided to publish the paper along with the rebuttals of the paper.
So the clustering curve also becomes sharper and sharper as you go larger?
I think the clustering curve remains a bit gradual. Okay.
Yeah.
So the sharpness is actually happening in the average path length behavior. The clustering probably remains smooth. Okay. Okay. Now, what Watson Strogatz did was that they not only showed this in a theoretical model, they also started looking at real world networks and asked, do real world networks actually have this property? That is, their clustering is like that of a regular graph. That is, if you take a real world graph and if you compare it against a equivalent random graph having the same number of nodes and links, you would expect some clustering, right? And you'd expect some path length. So the question is, how does the clustering of the empirical network compare with that of the equivalent random network? And how does the path length compare with the equivalent random network? And they showed that for a large class of such real world networks, it actually has the clustering much higher than what you'd expect from a corresponding random network, but its path length is kind of similar to what you'd expect from an equivalent random network, and so therefore it has this small worldness property. Okay. So so this is the conclusion they had, that many biological, technological and social networks have connection topologies which actually have this small world character. So in their own paper, they kind of looked at 3 different real world networks. So as a proxy of a social network, they looked at the collaboration network of movie actors. So in other words, if person X and person Y has acted in the same movie, there's a connection between them. So actually this is a derivative of this famous game called 6 Degrees of Kevin Bacon, which used to be very popular, I think, in the 80s or the 90s in student communities. So the idea was that, how many of you actually know who Kevin Bacon is? Okay, 1 person. Seriously? That, the vagaries of fame. So Kevin Bacon used to be, in the 80s used to be a, well, if not a superstar, at least, reasonably well-known actor. So he made his break in this movie Footloose, which was, a movie which popularized breakdancing. And then he has acted in a number of movies like, The Hollow Man, which is an adaptation of The Invisible Man. So there he played the villain and so on. In the 80s and the 90s, he could be seen in lots of movies. And so the, US undergraduates decided to invent a game where they said that, okay, Kevin Bacon seems to have acted in a lot of movies with lots of, variable cast and so on. So, presumably he's kind of central to the network of actors. So now we can ask, okay, how do you go from, let's say, what is your Bacon number? Okay. So Bacon number, if you have acted directly with Bacon in some movie, your Bacon number is 1. Then if you have acted with someone who has acted with Kevin Bacon, your Bacon number is 2. And then they generalize the game to say that, can you actually find the Bacon number of some arbitrary actor? Okay, so I think in the 98 or 99 and so on, when networks had just hit the market, as physicists were getting into this, I remember Professor Ravindra Amritkar, formerly of PRL, was telling me that he had a student who got very excited and started measuring the Bacon number of various Bollywood actors. So apparently Madhuri Dixit had a Bacon number of 4 or 5 or something. Okay, and I think interestingly this thing, the long range connection, so to say, was I think was it I think it was Rajnikant. So Rajnikant has acted in a, well, okay, I am a fan of really trashy movies, okay. So Rajnikant has actually acted in a movie called, I think, Blood Diamond. Has anyone seen that movie? Nobody has seen that movie. Sorry? Sorry? No, this is not that Leonardo DiCaprio movie. So this is a really trashy movie in which Rajnikant, he plays this auto rickshaw driver, a role he has played to perfection in many movies. And the plot is that so there's this. Oh, I'm sorry, it's not Blood Diamond. I think it's called Monsoon. Yeah, so sorry. I just completely confused. So the idea is like long back, like 300 years back in Goa, two lovers kind of, committed suicide, and they left behind some jewel. And in the present era, some American guy has come to Goa because he has heard of this legend that they had left behind some precious jewel, and so he has to find it. Okay, and Rajnikant is this auto rickshaw driver he meets, who helpfully, and it has all the Rajnikant antics, right? So like he throws this cigarette and then catches it in his mouth and so on. I mean, so it's hilarious, in a way. But the point is that it has this few, Hollywood C-grade actors, okay, who really had no job in Hollywood, so they just got them to play the white guys in this movie. So it's through this, you can actually connect Madhuri Dixit, because Madhuri Dixit acted with someone who acted with Rajnikant, and then Rajnikant acted with C-grade actors who happened to be, extras in some Hollywood movies in with some big name actors, and so that's how you get a, Beckon number of 5 for Madhuri Dixit. Okay. Anyway, so what Watts and Strogatz did was they looked at this network. So it had about 200,000 actors in this database, where the average degree was 61. So on average, each actor, over their career would be collaborating with let's say 60 other actors. So remember, this is not a single movie we are talking about. Okay, so in your entire career, you'd be, let's say, acting in, I don't know, 25 different movies, and we are talking about all the various, actors that you'd be associated with in your career. And then they worked out the average path length of this network, which was not too far from a corresponding equivalent random network, which is the same number of nodes and average degree. So you can see that both are around 3. Okay, but if you look at the clustering coefficient, it's vastly different. So for the random network, it's like minuscule compared to the clustering coefficient for the real network, which is actually pretty high, as you can see, 0.8. The maximum clustering coefficient is 1, right? Similarly, they looked at some technological networks. So here they consider the power grid. Then they consider biological network, which is the neural network of this worm called Sinorhabditis elegans. And then later on, other people looked at, for example, co-authorship networks. So if you have written a paper with someone, then you have a link with that person. So it's pretty much like the Erdos number, right? But you look at different kinds of, so for example, you look at archive, you look at SPIRES, which is the particle physics analog of archive. You look at the math reviews, list of co-authors and so on. Then you look at the metabolic network of E. coli. You look at food webs. You look at co-occurrence of words. In all of these cases, you find that the average path length is actually fairly close to what you would expect for the corresponding, random network having the same number of nodes and links. But the clustering would tend to be much higher than what you would expect from the random network. And on the basis of this, they claimed that most networks in the real world actually have this small world character. Okay. In fact, it has now become such a truism. Actually, why now? I mean, even 10 years back, if you found a network which was small world and you tried to send it to some journal, the editor would send back a note saying, if you actually send me a paper which shows that the network is not small world, then I'll publish it. Okay. So it's like almost everything that we know of is almost small world. Okay.
So this one, suppose the sizes are different, but if I normalize it somehow,
Yeah.
these numbers, they are universal or?
Which numbers?
No, these different columns for different things, let's say co-authorship or movie actors. These are for very different sample.
Yeah.
But if I normalize it with the size, somehow this, let's say, average path length or average degree, do they become universal, some kind of?
I don't think so.
No,
no,
like
no.
because so they don't grow like average path length. They don't grow like log n for each. Like this one is probably log n, right? This L random.
Yeah.
Right. So if I divide that log of that size.
Yeah, but it just grows as log n, but there's also coefficient.
Coefficient. So
right? So that coefficient would be different for different.
So there's no universal.
No. So because the coefficient would change the actual numbers,
Okay.
so it won't fall on a
Okay.
there won't be a data collapse.
Okay.
I think that's what you're suggesting. Yeah.
Okay.
Yeah. So the way that so now this depends upon how you construct it, right? So the way that Watson-Strogatz constructed it, as P becomes larger, it should follow the Poisson degree distribution. Okay. So of course, in P equal to 0, you should have a delta function, but the moment P becomes finite, it should start following a Poisson. Okay. Now.
So that's the large n limit, is it? For
Large n limit, right? Right. Well, not. By large n limit, you don't mean P. Do you mean P or do you mean N?
I mean n going to infinity.
Yeah.
For any P, it's Poisson. Is that what you're saying?
The moment P goes to 0 plus,
Yeah.
okay, for n tending to infinity, it will start showing a Poisson distribution. Yeah. So that would have been a natural launching off point for the next topic that I wanted to talk about, which is scale free. But what I decided was to actually flip, because I didn't manage to, finish all the stuff yesterday itself. So if I was doing this yesterday, I would have then next gone to the degree distribution business, because it turns out that real world networks often don't have Poisson degree distribution. They mostly tend to have exponential, but exponentials don't really set your heart pumping. Physicists really want. Physicists only get excited if they hear the word power law, right? In fact, once an ecologist collaborator of mine asked me, tell me something, what is it about power laws and physicists? I mean, why do you guys always get so excited about power laws? I mean, for us, it's all the same, right? I mean, exponential, log normal, and so on. But physicists seem to have this very special obsession for power laws. So, so power law degree distribution was something that caused the next big bang in network science the very next year, 1999. So this paper by Barabashi and Albert came out, which led to this whole scale-free network business and so on. But what I decided to do was actually flip my lecture. So basically, I'll now take up scale-free network tomorrow, because I will be clumping it along with the concept of structural balance in networks, because both belong to the topic of how networks evolve, or dynamics of networks rather than dynamics on networks. How does the structure of the network evolve with time? Okay. So I will discuss them together in the next lecture. Today, I will still stick with structure rather than dynamics of the structure, or I will stick with description of structure. But now I will change my scale. So from looking at local and global, yeah.
No, so basically it looks like the path length is more or less like the random network.
Correct, yeah.
That's because, I mean, few small
Exactly, a
connections
few long range connections can essentially
make
turn
you
it
better
into,
connected.
exactly.
But the clustering is, I guess, a more local property.
Clustering is a local property.
And so it's probably close to the regular, I mean,
yeah, so clustering can be way higher. I mean, it need not be, see, the underlying network is not a regular lattice,
yeah.
okay? But it means that many of your neighbors are also mutual neighbors. So the So the neighborhoods tend to be highly interconnected. Okay.
So you said most real-world networks are exponential, or did you say power law? I forgot.
So I'm going ahead of my story.
Okay.
But this is a, as they say, spoiler warning. Okay. So it's physicists love to see power laws even when none exist. Right? It's true. So so when Barabashi and Albert's paper came out, there was a mini industry of papers which saw power laws everywhere. Okay. So you take up any paper on any network, and there will be a line saying power law. So much so that even in about 6 years back, some guy came to our institute to give a talk on networks, and he kind of had a degree distribution which looked like this. Very optimistically, he drew a line and said, it's a power law. So it's partly because Barabashi is a very convincing salesman. Okay, so he managed to convince the entire world that power laws is the only way real networks behave. But then inevitably a reaction set in, and now I think the opinion has swung to the opposite pole, where people are saying that there are so few actual power law networks that it doesn't even make sense to study them. I mean, they're the exception actually. Okay, so most real world networks turn out to have either exponential or in actually many cases stretched exponential or log normal distributions, which it turns out can be very easily confused with power laws if you're not looking over a large range. As Newman famously said, any graph, when you look at a small enough region, would look like a straight line, right? And that's pretty much what had happened with this whole mini industry of power law networks. People started looking at 1 decade or 1.5 decade over of the degree distribution in a log-log scale. And of course, anything in that short range would look like, if you squint at it hard enough, it will look like a line, right? And so they claimed. So now, if you try to claim a power law, you have a much higher barrier. So you have to do, this maximal likelihood estimators and so on. So no, physicists are, I can say this because I'm a physicist. Physicists are terrible at statistics, right? So the only statistics we ever did was in physics practical classes when we had to draw some, line fitting in our experimental data points. So first of all, most of those data points were cooked up, as we all know. And then, you take the graph and you ask your friend, okay, let's look at it this way. Okay, let's fit the line, and then you draw a line, right? So that's the amount of statistics we used to do, right? So this is shocking to people in other sciences. Like even biologists know better statistics than us. Okay, so when we start claiming power laws, why even? I can say this because my wife is a biologist and I love needling her on this. I mean, like physicists are superior people than biologists, right? But yeah, look, I don't genuinely believe this, but this makes for a good, way of needling my wife. Okay, yeah. So now, if your paper goes for review and it just happens to end up with someone who's trained in social sciences or trained in biological sciences, they will give you hell. Okay. So nowadays, if you want to claim a power law, you better have a maximum likelihood estimator of ready and so on. Okay. All right. And that, of course, has revealed that many of the original networks which are claimed to be power law are actually not power law. All right, so now in the remaining slightly less than 1 hour, let me go on to the content of my next lecture. Yeah, so This is going to be about meso-level properties of the network or intermediate level properties of the network. So far I've talked about global properties and local properties. Okay. So you remember this figure. So I had shown that, you know, when you characterize properties of a network, you can do it at many scales. You can look at micro level properties. You can look at macro level properties. And I had said that, but there could also be intermediate level structures. So this is what I am calling meso. So what kind of properties are these? So, you know, you might be interested to ask, could there be groups of nodes which are talking to each other a lot, but there is very few conversations between such groups? Okay. Now, why is this treated as a separate property from the macro and micro? That's because you could have networks which could have the same macro property. So in other words, they can have the same average path length. They can have the same degree distribution. They can have, you know, very similar motifs. So, you know, like same micro level properties. And yet one may have complete homogeneity in the sense that there is no group structure. And the other network might have, you know, such strong group identities for different nodes. Okay. So you could have same micro and same macro properties, but it may differ in the meso level property, and this makes for extremely interesting differences in their function and in their dynamics. So that's why meso level properties are very interesting and important to study. So another reason for doing mesoscale analysis is that this allows us to study complex systems which otherwise would have been horrendous to kind of, you know, try to analyze in any way. Okay. So in a sense, it's a way of coarse graining the complexity of such systems. So we don't deal with the elementary components, but rather the clusters can be taken as now the elementary components, and we can look at the interrelations between them. So it's a bit like, you know, if you're an engineer, then instead of looking, you know, into a computer in terms of the individual resistors, capacitors, and other such elementary units, you might want to bunch all of them into functional blocks. So you might want to look at, you know, so in the coarsest level, a computer would be just this, you know, a block which corresponds to input device, a block which corresponds to a central memory store, control unit, CPU, arithmetic unit, output devices, maybe some secondary store, hard drives, and so on. Okay, and then each of these could be then further subdivided, and you could ask, okay, there are some integrated circuits which make up each of these, and then each of these integrated circuits, for example, would have a description in terms of, let's say, resistors, capacitors, and so on. Okay. So this mesoscale analysis allows us to, for example, look at a simplified or a more coarse-grained description which might be more amenable to analysis than otherwise. Okay. Now this slide was originally intended to, you know, like allow a smooth transition from when I talk about degree distribution in the context of scale-free network to this meso-level property. So now that I've flipped it around, this might suddenly seem that, you know, I'm taking my story, so I'm talking about something which I've already not introduced, so I'm sorry about it. But I still thought I would include it because this gives you some hint about how to, when you look at something like degree, which you might say is a local property, or a degree distribution, which you might say a macro level property, from there, how you can actually go to a meso level property. So for example, you know the degree distribution of a particular network, but sometimes knowing that is not enough. You might want to know about correlations between those degrees. So what do I mean by that? So if you are a very popular person, would you be more likely to be connected with other popular person, or would you be more likely to be connected to people who are very shy? Okay, for example. Okay, so is the degree of node I, which is connected to node J, is it correlated with the degree of node J, or is it anti-correlated with the node of degree J? Okay. Now, for a random network, by definition, there is no correlation because you are just putting links at random. Okay? So you don't expect that the degree of I and the degree of j, where I and j are connected, has any relation whatsoever. But that is not the case for real-world networks. So in real-world networks, we often find that there is some kind of correlation, either positive correlation or negative correlation, between the degrees of the nodes which are connected. So in social networks, for example, we often see that popular people tend to form a group of their own. So if you are highly socially gregarious, you tend to have lots of friends who are also highly socially gregarious. So here, like prefers like. So high degree nodes prefer to connect to high degree nodes. But there are other situations, particularly in technological networks and biological networks, where the opposite is true. So in a high degree node, actually preferentially connect to low degree nodes. So for example, protein which is highly promiscuous, which can bind with lots of other proteins, typically tend to connect to proteins which don't actually connect to many other proteins, okay, and so on. And this is also true, for example, I think in ecosystems where omnivore often feeds on lots of specialists and so on. So can we quantify this somehow? Okay. So this quantification goes by the name of assortativity. So assortativity is of course a very general term. It need not just refer to degree. So assortativity means that when individuals prefer to associate with similar individuals, okay, as indicated by this cartoon. Okay. So the opposite of that, disassortativity, is when dissimilar individuals prefer to associate with each other. So this similarity need not be a network property. It could be something completely different. So for example, people in this school, people from the same institution may prefer to hang out together. Okay. So here the assortativity is in terms of institutional affiliation. Okay. Or there could be gender assortativity. Okay. So young ladies might want to prefer to hang out with each other rather than with men of their age. Just giving an example. Or it could be the other way around. Okay. So this is an example of how you could have assortativity or disassortativity associated with certain intrinsic character of the individuals. For networks, we are often interested in how the assortativity is associated with a network characteristic, and the one that is most studied is degree. Okay. So what you could do, for example, is you can look at the correlation between the degrees of the connected nodes. Okay. So this is such a correlational measure, and if this correlation measure R, which goes by the name of assortativity, if it is negative, then you say that the network is showing disassortative mixing, whereas if it is positive, it basically says that you've got assortative mixing. So in this case, nodes prefer to connect to unlike nodes. So nodes of high degree mostly have neighbors of low degree. Whereas here, like prefers like, so nodes of high degree mostly have nearest neighbors of high degree. And while this is seen in biological and technological networks, we see assortative networks typically in social networks. Now, let me point out that when I say nodes of high degree mostly have nearest neighbors of high degree, you need to be a bit careful, because if you have a high degree, so if you are connecting with hundreds of other nodes, then just by random chance, you're going to connect to lots of other high degree nodes, because the probability of being connected to each other is actually proportional to the product of your degrees. Okay. So obviously, if Ki is high and Kj is high, the probability that I and j would be connected would also be high, right? So what we are talking about is that whether that probability of connection or the frequency of such connections is higher than what you would expect by pure chance. So it should be even higher than this number that is given by the product of Ki and Kj. Okay. So just by visually, if you see something and you say, okay, all the high degree nodes tend to be, seem to be connected to each other, so this is an assortative network. No, you can't say like that. you actually have to do a comparison that compared to random chance, is it connecting even more frequently to high degree nodes? Okay, so that's why you need quantitative metrics. Okay, now what do such networks look like? Okay, so if you look at a assortative network which has positive correlation, typically it will look like this. So you have a central core of nodes which have very high degree, which are all connected to each other. Okay, and then in the periphery you have nodes which have one or two connections, and they're kind of loosely connected to this internal highly connected core. By contrast, if you have negative correlation, or if you have disassortativity, you tend to have lots of, as you can see, star modules. Okay, so this is sometimes called a hub and spoke module. So you will have nodes which have this hub-like character where lots of low degree nodes are coming out. So this basically shows that high degree nodes are prefer to connect to low degree nodes, and then these hubs are kind of connected to other hubs, not directly but through other low degree nodes. Okay. So this is one way in which you might actually have a modular architecture. Okay. So in some sense, by having positive correlation, or assortative networks typically would tend to show what I would call a core periphery organization, and disassortative networks would tend to show modules where each of the modules have this typical star-like structures. And this brings us to this our main theme, which is what is the mesoscopic organization of networks. So how do you actually even start thinking about meso-level organization? So now we are no longer talking about the property of the whole network or the property of the individual elements. So one way to think about meso-level characteristics is that if you squint at the adjacency matrix, somehow properly arranged, do they show any of the following patterns? So if you have a structure like this, where you have blocks which have very dense connections, and then between blocks you have very sparse connections, that is indicative of what is known as a modular organization. Okay. So modules are basically nodes, groups of nodes which have very high degree of connection between them, or maybe very strong connections between them, and then relatively weak connections with other modules. Okay, so social networks, for example, are highly modular. So imagine that these are groups of friends, and they are having lots of social interactions with each other, and relatively fewer interactions with people in other social groups. Okay. Now, let's go over to here, where you now have you basically flip this picture. So basically the blocks now have sparse connections, and the connections between adjacent blocks actually have dense connections. And now you get networks which are hierarchical. Okay, so typically you would tend to see that there will be layers of nodes which would have few or no connections between them, and then but lots of connections with members of the next layer. Okay, so in the adjacency matrix, once you properly arrange it, would tend to show this kind of a property. Okay, and you could also have something like this. So basically, where you say that okay, it's not really a block structure. There is a highly dense region followed by a less dense or a sparse region. So by the way, I'm only showing this for the special case of just two modules or two levels, or just one core and one periphery. You can easily generalize this to multiple modules like this. So you could talk about any number of modules where this is dense and this is sparse. For the case of hierarchy, you could have so if you have multiple hierarchical levels, you could have something like this. Yeah. Okay. So this would mean that there are 4 layers and almost all the connections are occurring between these layers, and this has 4 modules. So there are lots of connections within these modules and relatively sparse. And then in the case of core periphery, there need not be just one very dense and the rest all equally sparse. So you could have, this is very dense, this is relatively less dense, this is even less dense and sparse. Okay. So you could have basically generalization of each of these. Okay. So in this particular case, what you have is basically a central group of nodes which are very well connected with each other. So they form the core, and the rest of the nodes have very few connections, and they loosely hang on to the network by connecting to the core. So sometimes you would come across something called the rich club characteristic of a network, or a rich club coefficient. So this is actually just another way of actually quantifying this core periphery property. Okay, so rich club is not all that different from the core peripheryness. Okay, so these are broadly the 3 types of meso-level organization that we tend to see in the world around us. So let's go through them one by one. Yeah.
So is the assortativity enough to distinguish between these 3 groups?
No,
or,
it's not. It's not.
So how do you, so given some adjacency matrix, do you, how do you, is there a single sort of recipe to find out which of the groups are there?
There is no single recipe, because as I will show that you could also have networks which have some modular and some hierarchical character.
Okay.
Okay. So you have to have different metrics for measuring modularity, for measuring hierarchy and measuring core periphery.
Okay.
Okay. Because you could also have combinations thereof. Okay. This is I'm just talking about a very simple case where exclusively it is of one type. All right. So first, let's look at core periphery. Okay. So let's take a network which looks like this. Okay. So you define the K core of a network as that subnetwork which contains all nodes that have degree at least equal to K. Okay. Now think a moment about it. Okay. So it's not like I'm saying that I'm considering all nodes which have degree at least K, because in that case you would just look at the individual degree sequences and you would say that every node which has degree higher than K or higher would actually correspond to the K core. No, that's not what I'm talking about. So okay. So if you look at a network like this, okay, this node has a degree of 1, 2, 3, 4, 5, 6, 7. Okay. This node has a degree of 3. Okay. But I'm not saying that this node is part of a 7 core. Okay. That's not the point at all. Instead, suppose I have a thing like this. Okay, so this one has 4, this one has 5, this one has 5, this one has okay. So I will say that this group of 6 nodes forms a 4 core, okay, because each of the members of this group has degree at least 4, okay. That's what I mean. So it's a property of a group, okay, not of individual entities. It's a property of how the group hangs together, okay.
Could it be disconnected?
Yeah, you could have multiple K cores. So for example, you could have another big core over here, for example. Yeah. Yeah.
Question.
Yeah.
So the node which is connected, which branches out at the corner, right? In your diagram, yeah.
Yeah.
So you will count that as 4, not as 5 when you look at the subnetwork.
No, so here I was just talking about what is the degree of this. So if you want to talk about the degree, okay, you have to consider all the connections it has.
I thought not the subnetwork, but all the connections.
No. So yeah, so when I'm talking about the 4 core, what I'm saying is that this group is defined by the fact that every node has degree 4 or higher. Every node in this group.
Let's say that one had like the diameter connected to that one. If you erase that,
yeah,
and connect one more somewhere else.
So it's 4. Let me erase that. Yeah.
No, not that one. The
Then?
diameter.
Which one?
The hexagon, the longest line in the hexagon.
This one.
This one, yeah.
Yeah.
If you erase that one,
Okay.
and maybe connect the other one to someone else, whatever.
Oh, okay.
And then would it, yeah, and draw 2 lines to the one, to that one.
Okay.
Yeah, let's say.
Yeah.
So when you erase, when you now look at that subgraph, now it will have, let's say, 3 nodes. So it won't be a 4 core anymore, right?
Very good point. So in fact, the recursive procedure of finding K core precisely does this.
Okay.
Okay. So just hang on, and I will just show you. Okay. All right. So there's a very simple way of actually. So you might say, okay, this is a very technical definition. Okay, I can understand you are saying that this is a core and this is a periphery, but can I have a simple recipe for finding the core? So one such technique, there are multiple techniques, of course. One such technique given in '83 by the computer scientist Seidman essentially thinks of this as an iterative procedure of peeling away layer after layer and trying to get to the innermost core. So you can actually, get a picture very similar to this kind of agency matrix that I was mentioning over here. So this is the innermost core, then comes the next layer, then comes the next layer, then comes the outer periphery. So how do you actually find that? Okay. So Seidman's proposal was, okay, so first, if you want to determine the K core, first you remove every node which has degree less than K. Now you check the network that is resulting from it. Now as a result of this removal, some of the nodes which originally had degree K or higher would now have degree less than K. So you remove those also, okay. Then you again check, okay. Now as a result of those removals, if there are some nodes which have degree less than K, you remove those also. So keep doing this until you find that there are no nodes which have degree less than K. So that becomes the K core, okay. So the one core of a network would simply be this, because every node has degree 1 or higher, okay. How do I find the 2 core? Any ideas? Okay, so 2 core means every node must have degree 2 or higher, right? So obviously this will go, 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 these two will go, this will go, and this will go, okay. So in my first pass, this is what I get. Okay. But now I realize that this, which originally had a degree of 2, has now a degree of 1. This also a degree of 1. This also a degree of 1. Okay. So this will also go. Okay. Now let's check. Is there any node which has degree less than 2? No, right? So this becomes a 2 core. Okay. So another way of thinking of it is that you have eliminated every node that do not form part of a loop. Okay. So all the nodes which were like sticking out like thorns have got rid of. So this gives you a generalization. So this says that that means there has to be at least k paths between any pair of nodes which belong to a k core. Okay. So you can also connect to k cycles and so on. Okay. All right. Now how do you get to 3 core? So obviously this has degree less than 3, this will go. This has degree less than 3, this will go, so will this. Okay. So let's delete them. Okay. Now the remaining ones, is there anything which is degree less than 3? Yes, no? Some people are not so sure. Okay. No, there is actually none. Okay, good. What about 4 core? Sorry? Exactly. So I heard someone say 2 nodes can be part of 4 core. That's impossible, right? Because you have to have at least 4 nodes in a 4 core. You know, if you have a k core, then it has to be at least k nodes in it, right? So yeah, there is no 4 core. So the 3 core is the innermost core, followed by a 2 core, followed by a 1 core, or you might call them shells actually rather. Okay. Example. So this is something that we'd been working on, about a decade back. So this was just after the 2008-2011 financial crisis, and as you know that this crisis was brought about by basically banks collapsing as a result of bad lending. Okay. So an economist who was working with the Central Bank of England was basically sharing with us some data about how banks do lending with each other. Now there's a problem with this because banks actually don't let out how much actually they are lending out to each individual bank. That's apparently highly confidential information. So they only tell you what is the total amount lent out to other banks. Okay. Now you get this information from all banks, and from there, by doing a kind of a linear programming problem, you try to estimate what might be the individual borrowings from one bank to the other. Okay, it's not a foolproof method, so there's a lot of margin of error in this. It's a under constraint problem, but doing this, you can actually build a network of how the banks are lending to each other. So what we realized was that this actually forms a very strong core, and the size of the banks basically refers to how much capital they have. So the big banks are basically these big nodes, and you can see that there's a lot of relations between them. So they kind of borrow and lend from each other a lot. Relative to that, there are a few another group of banks which have very few typical relations. So for example, there are a few big banks over here, and they tend to support some of the smaller banks. So this is an example of how you can have a core periphery structure. Another example that this is actually a fairly recent paper published in 2020 is of collaboration network in the film industry. Okay, so in this paper, what the scientists did was they looked at the collaboration network of not just actors but all the movie creators. So actors, directors, cinematographers, editors, writers, and so on. and found that the resulting network actually has a core periphery organization, and they identified so-called broker nodes. So what are broker nodes? Broker nodes are nodes which connect a large number of nodes in the periphery with nodes in the core. Okay. So they act as intermediaries. Okay. And a broker could of course be part of a core itself, or it may be also a part of the periphery, but its main purpose is to link peripheral nodes with the core nodes. Now, interestingly, what they found was that they correlated this with creative success. So, like how many awards have you won? That's a very bad indicator, you might say. But they found that there's a positive correlation between being a broker node and the number of awards you win. Okay. That need not have anything to do with creativity. It could just be the way social dynamics works, right? If you are known to a lot of people, next time some award is coming up and the committee is like deciding who to give it to, they might just say, oh, hey, I know, what about this guy? I know that guy, he's a good guy, yeah, I met him in that party last night, yeah, yeah, why not, let's do it. So it might just work like that also. Right? So clearly core periphery organization has lots of, interesting aspects, only part of which has been plumbed. But let's now push on to the other very important, Meso-level property, which I'll be actually spending the bulk of my time on, which is modules. So as I mentioned, modular networks are characterized by groups of nodes which have very dense interconnections within them and relatively sparse interconnection between them. Okay? And the reason modular networks are so interesting and important is because they're all around us. Okay? So, here I just show two examples of modular networks from two very different scales. So this is the metabolic network of E. coli. So these circles are not actually individual metabolites, but rather modules of metabolites. So if you expand these, there's a huge number of metabolites which are linked to each other, and the color actually refers to what is the function of the metabolites which are members of these modules. And as you can see that there are some modules which are clearly related to specific functions. So for example, this one is primarily related to metabolites which are involved in amino acid metabolism, and so is this. Okay? Whereas these ones, the yellow ones, are involved in carbohydrate metabolism. This one is primarily dealing with nucleotide metabolism, and this one is primarily dealing with metabolism of cofactors and vitamins and so on. So we find this often that modules which are purely defined structurally, you don't have any idea of what they do and so on. You just look at the relative density of connections within the module and between the modules, and you just construct the modules. But then the things that you end up with also tend to have certain specific functions. Okay? And then I have example from another completely different scale. So this is a food web. So you have certain species which have very strong interaction with each other, and this is another group of species which have strong interaction with each other, and there's relatively very sparse connections between them. Okay. Social networks, as I kept alluding, also tend to be highly modular. Now, this is a quite a unique data set in a way, because unlike most social network analysis that you see reported in the literature, this is an actual physical contact network. Okay, so for a number of reasons, getting information about offline contacts is pretty difficult because there are privacy concerns and so on. Also, as Ritom's data collection effort might have made it clear, there are issues with people simply thinking, oh, it's too much bother, why should I report it? Or people might just forget that, they met someone and so on. So if you do this old style, pen and paper survey where you send out people saying that, okay, who do you know? Okay, so there's a lot of misreporting or non-reporting and so on. And so people have therefore gone on to look at online networks. The online networks are actually very easy to get data from, right? Because these are all actually recorded in some big database somewhere. So you don't have to worry about people forgetting or people hiding some data and so on. So if you manage to be friends with some big executive in Facebook or Twitter and so on, you can actually get a hotline access to all this data. Okay. The problem is, of course, convincing them that you are a genuine enough person and it would be of some use to them. But once they are convinced, you can get this data. So, for example, Niloy Ganguly and his group at IIT Kharagpur have been doing a lot of work on Facebook, Twitter, and all these kinds of databases. Okay. But the problem with social network is that, or online social network is that, sometimes these links don't really mean that there's a meaningful relationship. I mean, it doesn't cost you anything to, say that you like someone. You may not have talked to this person in years, right? But you still follow that person, right? So it may not be indicative of actual investment, okay? By contrast, offline social networks, in order to maintain them, you actually have to, do a lot of effort. So luckily for us, there was this database of several, villages in southern Karnataka whose social networks were mapped out by this NGO called Bharata Swamukti Samasthe. So the reason why they were doing this was, of course, nothing to do with network science. So they were basically trying to see the potentiality of starting microfinance initiatives in these villages. And so one of the things about microfinance is that you want to know whether the money you lend out has any possibility that the person will actually pay it back. Okay, the money, for all you know, this person is going to just go to the local, arak shop and just blow it away, right? So your idea is that, look, if this person is connected very strongly to the social network, there might be some leverage on this person to pay back the loan. Okay, at least if this person loses all that money in their business venture, maybe their relatives or friends will chip in to lend back the money. So you are much more likely to lend it to a person who is very strongly connected to the social network rather than to some loaner, right? So a loaner, once he's blown the money, there's no one the person can turn to pay it back. Okay, so it has to be written off as a bad loan. So there are practical reasons why they did this social network analysis. Unfortunately, after they did this sped work, they spent so much money in doing this research work, they just went out of business. Okay. Fortunately, before they went out of business, somebody got hint that they had this data. In particular, Abhijit Banerjee, everybody of course knows about Abhijit Banerjee. He won the Nobel Prize, I think, a couple of years back. Abhijit Banerjee and his group, including Esther Duflo, his wife and co-winner of the Nobel Prize, managed to get hold of this data. Okay, so, and luckily for us, they decided to put it up publicly on the web. So you can actually just get hold of this data. You probably have to write to the person who maintains the database that this is what you would want to use it for. But mostly if you are just doing it for research, they will just allow you to have this huge database. It's a fantastic database in the sense that, what I'm showing over here is just one village. Okay, of course, for anonymity purposes, none of the villages are named, none of the individuals are named. So it's just, for us, we just know it as village 55, okay? So this is a population of, 1,000, slightly upwards of 1,000 individuals. And the largest connected component is slightly less than the population. So there are a few fragments, or at least those people probably didn't report the connection they had with the rest of the people. It's unlikely they will be completely fragmented, but anyway, what can you do? And you have the data in various planes. So they just didn't go and ask, okay, who do you know? They would go and ask questions, okay, who are your family members? Okay, so that would form one layer of the network, the family relations. Then they would ask, okay, which shops do you go to? Okay, so commercial transactions would form another layer. Okay, then which temple do you go to pray, or which mosque do you go to pray? Okay, and they will find out who are going at the same time. So if you go to read namaz at around the same time, presumably you'll be meeting with each other, right? And so that's another religious gathering and so on. So in this way you have like 10 or 11 different layers, okay, different kinds of social relations. All right. So the data set is very rich. You can do lots of interesting things with it. We did something very simple. We just collapsed all that data and just said, no matter which layer you are, if there's a connection, then you are linked, okay? And you get a network like this. And then what we did was, and this is something I'll come to, we used a particular method. So this is this spin glass similarity handling method, but I won't go into the nitty-gritty details of it, because I'll just barely refer to how you actually find modules. And we found the modules. And it's rendered in such a way that the people belonging to various modules are colored in the same color, and you can also see that they also tend to be highly clustered. So we find that at least using this method, we can group it into 25 modules, the largest having 127 individuals, with the mean module size being about 50. Okay. So each of these groups of people who are strongly interacting with each other is roughly about 50. Okay. Now, this brings me back to something that I spoke about in the very first lecture. Remember the Dunbar number. So it's interesting that the largest module is actually close to the Dunbar number. Okay. So the number of people you have meaningful relationships, is not higher than 150. I mean, of course, 150 was just an estimate, right? So it need not be exactly 150. So actually, that's fairly interesting. So, so this is just an example. I'll come back to this particular network later for some interesting stuff we did. But this raises an interesting issue, right? I showed modules, but you might be asking, how did we find the modules in the first place? Okay. So it's a non-trivial problem. Okay. Why? So, how do you divide the nodes of a network into groups such that nodes in each group are densely connected or strongly interconnected? So suppose you have a network like this. It's a no-brainer that this group ABCDE and FGHIJ are within themselves very densely connected, but between these groups there's only one link, namely D to F. Okay. So if you look at the adjacency matrix, it will look like a block diagonal matrix. So essentially you'll have, if you arrange them as so A, B, C, D, E, F, G, H, I, and J, then A to E will form one module, so this will be highly dense, this will be highly dense, but they will be not completely disconnected because D to F, okay, so A, B, C, okay, maybe here. So this will be 1, and similarly this will be 1, okay, the rest are all zeros, and so on. Okay. So you can clearly see that this has this block diagonal form that I was saying characterizes a modular network. But the problem is this, that if I now scramble this network, scramble this matrix, so I keep interchanging rows and columns, the matrix is, the number of, the links are actually still the same, okay. I'm just scrambling the rows and columns. After some time, I'll get a matrix where this block diagonal character is completely lost, even though the links are still there. Okay. How do I unscramble it and get back this block diagonal form? That is the problem of how do you determine modules or how do you find communities. Okay. Now you might say, okay, why not draw the graph? Okay. So if I draw the graph, it will sometimes be visually clear. The problem is that if you have a network which has 1,000 nodes, okay, or for that matter, the previous social network I showed, okay, if I just plotted it, there's no way you would be able to figure out what are the modules. Okay. So clearly we need a quantitative way of finding the modules. So this forms a whole subarea of its known, and it actually predates the current interest in networks. So in the 1960s, computer scientists got interested in this problem, that how do you actually divide the nodes of a network into non-overlapping groups such that the number of links between the groups is minimum. Okay. So that essentially is nothing but asking what are the modules. Yeah.
So, okay, so we have in the sparse region of the block, so we have 1, 1. I mean, let's say I keep adding ones in those sparse blocks. And when, like, what is the proportion of ones until I decide it's not actually in modular form? I mean,
yeah, so you can actually do that exercise. I will actually talk about that in like just 3 slides maybe.
Right.
Okay. Just hold on.
Yes.
Okay. All right. In fact, that's precisely something that we did. Okay. All right. If I forget, just remind me. Okay. All right. So so basically, then the question is this: how do you divide the nodes of a network into several groups such that most of the links are within groups and the fewest links are possible are between groups? So this is sometimes called module detection or a community detection and so on. And almost all the algorithms that have been developed are aimed at precisely this. Where they differ is how do you define most and how do you define few. Okay, that just by altering this way you define most and few, you can get different algorithms. So how do you measure modularity? How do you say that this is more modular, this is less modular? So how do you assign a number? So like going back to my second lecture, something becomes a scientific quantity only once you can start measuring it, right? So how do we measure it? So one of the big developments of this field came when Mark Newman in 2004 proposed a measure like this. Okay, so he said that, look, suppose I happen to know by magic the true module partitioning of the network. Okay, how I know it, we'll come to that later. But suppose I know this, then I can find out how modular the network is by using this metric, which is essentially asking, compared to the probability that just by chance 2 nodes in a module would be connected, what is the actual frequency with which they are connected? So remember, the probability that if you have degree I and another person has degree j, the probability that you two will be connected is proportional to the product of the degrees, ki, kj. Okay? So this divided by twice the number of edges is basically the probability that just by chance these 2 nodes would have an edge. So this is just the random chance. Okay? Whereas Aij is the empirical value that a connection actually exists. So this is the the true matrix, connection matrix that is there. So this difference tells you how likely is it that this would have happened by chance versus how unlikely it is. Okay, so the bigger this value, the more the surprise if a connection exists. And then you are saying that you are only, considering this particular term if I and j belong to the same community. So a delta function Ci Cj, which is 1 only if I and j belong to the same community. So basically you are asking that compared to just by chance of two nodes in a module being connected, what is the actual frequency with which two nodes in a same module are connected? The more the difference between the actual value and what you expect by chance, the more modular the network is. Okay? That is the concept. All right? Now, for a random network, since each of the connection is by definition occurring by chance, so Aij terms should actually be proportional to Ki Kj. So by definition, it should be very close to 0. Okay? So the connection density within a module should be same as the connection density everywhere else. So you should not see this block diagonal structure at all. You should just see homogeneity. Okay? Now you can also generalize this definition to directed and weighted networks. So instead of Ki Kj, now you are talking about the strength or the in strength of the ith node and the out strength of the jth node. So remember I mentioned, I think in the tutorial day before yesterday, that the strength of a ith node is the sum of the edge weights of the ith node. So basically if you don't have weights, this simply becomes the degree. So for an unweighted network, this will simply become the in degree of the ith node and the out degree of the jth node. Okay? Now you can use this measure to essentially find how much modular a particular network is given a particular guess about what are the modular partitions. And that is precisely where the problem lies, because it's like putting the cart before the horse, right? I mean, you are saying that, okay, in order to find the modularity of a network, I already need to know what are the modules. So how is this possible? So suppose I just, make an arbitrary guess that, okay, these belong to this module, this belongs to this module, and so on. So obviously my Q measure will depend on that, right? If I make another arbitrary guess, my Q measure will become different, even though the network is the same, okay? So Newman turned this weakness into strength. So he said, we can actually use this to find the true modular partitioning by the following. We say that start from an arbitrary guess, okay, you'd get some Q value. Then you make a small change in this guess, you make an improved guess. And so what do you mean by improved? If the Q that you calculated with this new guess is higher than the Q that you got before. So then you say this is a more improved guess. And then you make another guess, and if it turns out that this new Q value is higher than the previous Q value, then you say, okay, this is a better guess, so I'll accept this. So you see where I'm going. This is nothing but the problem of combinatorial optimization. Okay? So now once you have turned this into a problem of combinatorial optimization, you can use your favorite optimization routine. You can use simulated annealing, you can do gradient descent, you can use whatever you want. Those are all ready-made algorithms out there. You can just let it run on this and use this optimization routine to basically maximize Q. And once you can't maximize Q any longer, that particular guess of the partitions is apparently close to the true module. Okay? Now you might say, well, how can I be sure? Okay? Yeah, well, the thing is that the only way to be sure is do a brute force calculation where you try out all possible partitions. But as you might imagine, this is a computationally very hard problem. In fact, it's an NP hard problem. Okay? So this question of how do you actually find the modules, again, is one of the big challenging problems of network science. There are many methods which have been proposed, some better than others. So,
so do you always accept, or you accept with some probability when Q is?
Yes. So if you are doing, like, for example, simulated annealing or some stochastic gradient descent, then you can use Monte Carlo methods like that. So you say that, okay, if Q increases, I will accept it, but if Q decreases, I will accept it with some probability which is proportional to some temperature. Okay, so this is just to ensure that you don't get stuck at a local minima. Yes. Okay, so yeah.
So is this problem sort of related to the question how many bonds do you have to cut in order to make the graph disconnected?
Very good. That is precisely how the computer scientists approach this problem. So remember when I said graph partitioning was popular in the 1960s in computer science literature, that's precisely the question they asked. They said, how can I divide, in the simplest case, how can I divide the nodes into two groups such that the number of bonds between these two groups is the minimal. In other words, the fewest number of bonds I need to cut to disconnect them. Yes. So that is in fact in spectral partitioning, which is another method of trying to find modules, that is precisely the question that is being asked. Okay. The problem with spectral partitioning is that it's very well defined for dividing a network into two parts. Okay. Now, if a network has m parts, m modules, how do you do it? So computer scientists will say just do, keep doing it. Divide into two parts, then take each of those parts, do spectral partitioning, and keep doing this until you cannot do this anymore. Okay. The problem with that is getting stuck at a local minima. Maybe you would have got a much better modular division if you had originally started with the idea of dividing into three modules. And so, if you just divide into two modules, maybe part of the third module is part of first module and part of the second module. So now you are stuck, because your original sin of having divided module 3 partly into module 1 and module 2 will now remain with you, right? Yeah, I mean open problem in the sense that there are very good algorithms, but the market is still open for better and better algorithms. Okay, so if you can come up with your so currently there's this big contest between what they call actually this one, the Roswell-Bergstrom method, the InfoMap method, and the spectral method of Newman revised with simultaneous. So basically use a simultaneous method to try to maximize Q. Okay. So are you familiar with simultaneous? Oh, okay. So the idea is simply this, that let's say in the space of all possible graph partitionings. So of course this is a high dimensional thing. I'm just just for fun drawing it as a two-dimensional landscape. Okay, but imagine each point corresponds to a particular partitioning of the network into modules. Okay, so suppose I represent that in a two-dimensional plane, a continuous two-dimensional plane. So there are certain solutions which have high values of Q, right? So what you're trying to do is you're trying to reach the highest peak. Okay, now the problem is this, that if you use a method where you say that I will accept a particular new partition only if the Q value is higher, okay, then you will reach some local hill and be stuck, because any move that you make is going to make your Q worse, right? So how do you actually end up here? Okay, how do you avoid? So this is called the problem of local maxima. Okay, you tend to get stuck at a local maxima if you do a very strict thing like that. So instead you say that, okay, mostly I will go upstream, go uphill, but occasionally with a small probability I may also choose downhill. Okay, now the question is, how often do you choose downhill? Okay, so you can actually use a Boltzmann factor. So you can say that the difference in delta Q divided by, let's say, KT. So instead of energy I'm using Q, right? So if my move tends to decrease Q, I will tend to accept it with some probability which is proportional to this. So obviously if temperature is very high, then I wouldn't care about Q at all. With equal probability I'm going to go anywhere. Okay, but if T becomes 0, that means I can only go there if Q is going to strictly increase, right? So by varying T, you can now basically with various probabilities tend to also take downhill moves. Now, you might say, okay, but what is my correct T? Okay, how do I find the correct T? So in simultaneous annealing, what you do is you start with a very high T and you very slowly start decreasing T. The idea being that initially, you are basically jumping around your landscape. Okay? But as time progresses, you are getting more and more localized. So if it's a shallow hill, then with a high probability you will jump out. But if it's a tall hill, then you tend to get stuck there. Okay? So there's a proof which says that if temperature is cooled infinitesimally slowly, it's guaranteed to give you the global minima. But of course, we cannot do this infinitesimally slowly. So in practice, we have to use something like a cooling schedule. And people who do simultaneous annealing have various kinds of heuristics to figure out what kind of cooling schedule is better than others. Okay. Okay. So I'm actually now completely out of time. So I'll actually stop at this slide just by saying something about this. So this is along with simultaneous annealing method, the other big competing method for finding communities is the information flow method. So unlike most methods for finding communities which depend on maximizing Q, this takes a completely different approach. So this says that, if the network has some intermediate level pattern, I mean module is a pattern, right? It's a structure. So suppose I want to compress the information about the network. If there is any pattern in the data, I can always use the pattern to compress this information. Okay. If you are familiar with data compression techniques, you know that what people do in order to compress data when they want to pass it across is to look for regularities or patterns. So for example, suppose you want to send some information across a data channel. Okay. So if it's a number like 010101010101 ... you don't actually need to send all these numbers, right? You just say repeat 01 so many times, right? So you identify a regular pattern and you're just using that regularity to compress this information. Okay? Same idea for networks. If there's a modular organization like this, okay, you actually don't need to send the individual zeros and ones. You just say that, look, here is a 1, everywhere else is 0. Okay? And here you say, here is a 0, everywhere else is 1. Okay? So you use that block diagonal property to compress this information about the network. So the idea is that you let loose a data compression algorithm on your network adjacency information, and you see how much it is compressing the information. The more compressed it is, the more modular it is. Okay? So that's basically the idea. So this idea was actually used by Roswell and Bergstrom to come up with a network community detection method. So what we did once was we actually used both the Newman kind of method and this Roswell-Bergstrom method on the same network which had a modular character, just to compare how similar are the modules, because they must be consistent, right? If the network is truly modular, in some sense, no matter what method you use, should give you similar kinds of modules. So what you will notice is that there is a difference in the sense that you get more modules out of the Roswell-Bergstrom method than the Newman method. But the interesting part is this. The many modules of the Roswell-Bergstrom method essentially is just splitting one module that was found by Newman's method into many submodules. Okay? So they are actually fairly consistent. Okay? It's just that one is looking at a much more finer level and one is looking at a slightly coarser level. So if you combine many of the Roswell-Bergstrom methods, you get one module which you get from Newman's method. Okay? So they are just looking at the thing at slightly different resolutions. Okay? But otherwise, if you have a truly modular character, the two methods actually are fairly consistent with each other. Okay, okay. So before, so again, I obviously have lots of other stuff that I couldn't say, but I did have a assignment for today. Yeah, so and this assignment, basically you can solve using whatever I have talked about today. So when Shonjib and Abhishek puts up today's slides, please go to the last page and try to solve this assignment. So basically the first assignment is on modules, and the BCD assignment is on finding core periphery. Okay? All right. So we will meet in the tutorial.
So in the previous class, we were discussing about biochemical pathway of E. coli chemotaxis, and we started we made this signaling diagram. So let me just draw it once more here. So this is receptor. Using some adapter protein, KW, it was connected, it was forming this receptor kinase complex, KA. Okay? KW was holding the complex together, the adapter protein. Then KA, in the active state of the receptor, KA would be autophosphorylated. It will form KAP. And then it will donate its phosphate group to two proteins. One is KY, which was called the regulator protein, response regulator. In the phosphorylated form, it becomes KYP, and this is activated by KAP. The dephosphorylation is controlled by another enzyme, KZ. This is another protein. And in the phosphorylated form, KAP will go and bind to the flagellar motors. And finally, that will control the run-tumble motion of the cell. This was the sensory part of the module. And this was the adaptation part, where KAP will donate the phosphate group to KB, which in the phosphorylated form, KBP would like to demethylate the receptors. And methylation of the receptors will happen by another enzyme, KR. So this was the adaptation part. We had discussed how this adaptation adaptation uses the mechanism of negative feedback to make sure that the activity of the receptor is never very high or very low. If it is so, then the negative feedback kicks in and bring the activity back to its average value once more. So, and to understand this adaptation, we were trying to come up with some simple description of this adaptation kinetics. And there we were, we used a very simple, perhaps the simplest possible mathematical description of this adaptation kinetics, and we found in that description the exact adaptation comes out to be some fine-tuned feature, such that if the biochemical parameters like the concentration of KR or the methylation rate or stuff like that, if these fluctuate slightly as they would do, as they are expected to do from cell to cell, then you lose the exact adaptation. So then, however, in experiments, exact adaptation is found, to be a robust mechanism. It is found in various different cells. So therefore, there was this, some other description was needed, and that was actually given by Barkay and Libler. So this is the next thing I will discuss. Barkay, Libler, robust mechanism for exact adaptation. This mechanism, as we will see, it allows exact adaptation over a very wide range of biochemical parameters. But even this one is also a very simplified description of the whole diagram. So here we assume the receptors have a single methylation site. Although an actual receptor has 4 methylation sites, and as we have I think we have discussed this already, that they are they are present in the form of dimers. So, but anyway, so multiple methylation sites we are not considering here. We are considering single methylation sites. So the receptors can be either unmethylated X or methylated XM, just like before in the previous description. And XM can also be present in active form, which we write as XM star. And the total activity of the system would be total activity, total number of active receptors. So the activity is just equal to XM star. Okay. And then we make one assumption which was also there in the previous model, that key R works at saturation. If you, okay, let me write it down once more, because yesterday I wrote it down. So this Michaelis-Menten equation I wanted to write down. So let me write it here. So this is, so the rate of product formation Vxs was equal to V times total concentration of the enzyme X, total the concentration of the substrate divided by some constant plus concentration of the substrate. When I say key R work at saturation, I mean that substrate concentration is very high, which is not unreasonable given the very small number of key R molecules and very large number of receptor molecules. So therefore, you can neglect this K, S gets cancelled. So it is just the rate multiplied by reaction rate multiplied by concentration of the enzyme. So this is what is meant by key R works at saturation. Second assumption, which is the crucial assumption here, which was not present in the previous one, it says that key B, the demethylating enzyme, can only demethylate active receptors. Key B works on active receptors. Therefore, key B can only work on XM star and make it X. X is always inactive, okay? XM star is the only active ingredient here, active component here. So, key B can only work on XM star and turn it to XM, X, but it cannot work on XM. XM is not a possible substrate. Although it is methylated, key B cannot work on it. This is one assumption used in this model. So therefore, according to this assumption, this is how I am describing the system. Suppose this is the receptor. I write receptor like this, and this is the receptor with methylation level, methylation group added to it, and this is the active part, XM star, and suppose this is the methylated but inactive form. Okay. So according to this, key A, key R will work on it and turn it into a methylated receptor, and key B will work on it and turn it into unmethylated and naturally inactive receptor, and this active receptor, it will give rise to tumble. I mean not active receptor, I mean it is the activity, it is active, therefore it will cause this phosphorylation of QIP, and finally it will give rise to tumble. And there is of course some flow transition between this active inactive state, particularly this transition. Just one second. This transition is controlled by the attractant. Is this diagram clear to everyone? This is unmethylated receptor, key R acts on it, make it methylated receptor. This is the methylated and active receptor, key B acts on it and bring it back here. There is transition between the, when the receptor switches its activity state, this is given by these two arrows. Particularly the active to inactive transition is facilitated by presence of the attractant chemical. That's all. Okay. This is the? Which is the run phase? Yeah, no. So, okay, I'm not showing run phase here. I'm just showing that when it is, run phase would be like this. Yeah. So, I mean run phase could be either, whenever it is active, it could mean run. Inactive, sorry, I'm saying all the wrong things. When it is inactive, this one or this one, because if you look at the diagram, when it is inactive, key AP is not formed, key YP is not formed, nobody is binding to the flagellar motors, and everything is rotating in the counterclockwise, and it is just running smoothly. Okay, so so this is the, so I wanted to emphasize this is the most crucial assumption, that key B works on only active receptors and not on inactive ones.
So
Run to tumble?
Is a two-step process in terms of
No. Even from here to here, it.
mean like from tumble to again to go to
Yeah,
the next tumble?
if you come this way, then it is one step. Yeah. Okay, so now let me write down the time evolution equation for the total population of methylated receptors. So ddt of xm plus xm star. That is equal to, how can it increase? It can increase because x being acted on by key R gives rise to xm, and that for that reaction key R works at saturation. So this is equal to VR times R minus, it could decrease because of demethylation, VB, demethylation rate, multiplied by concentration of key B, multiplied by concentration of active receptors, divided by K plus xm star. Here I have just used the Michaelis-Menten formula. So in steady state, this should be 0. So therefore in steady state, I have VRR is equal to VBB times xm star divided by K plus xm star. And the steady state activity call it A0 is simply is equal to total number of population of active receptors is equal to xm. So you can solve this equation and you can show that it is equal to K times VRR divided by VBB minus VRR. Okay, so this is the steady state activity. Now when you add attractant to it, there would be adding attractant facilitates this transition. So there would be a quick decrease in the population of xm star. Okay, which means that demethylation then becomes very slow. Not that because its rate is decreasing, but xm star is going down rapidly. So therefore, although this Key-B enzyme is there, it doesn't have any substrate to work on. So therefore, demethylation will almost stop or have a very small rate of progression, but this KRR is always present. So the receptors are going to get, all the time receptors are going to get methylated by this KR, but because Key-B can only work on active receptors, they are not getting demethylated. So methylation rate goes up, and which raises the activity. And the thing is, when the methylation rate goes up, when therefore it increases xm, the population of xm. Now xm star is some fraction of the total methylated enzymes. So therefore xm star also gradually increases. Is this clear? So now when the new steady state is reached again, the time evolution equation is ddt of is the same as before, ddt of xm plus xm star is equal to same methylation rate minus VBB xm star divided by K plus xm star, same equation as before. And the steady state activity therefore remains the same, A2 is equal to xm star. It is the post stimulus steady state, it is the same value, K VRR divided by VBB minus VRR. So notice that even this one or this one, the same expressions, they do not involve ligand concentration. So the activity, steady state activity is independent of ligand concentration. When you add ligand, activity momentarily gets down, but then it goes back again and comes back to that same value. So therefore, in this picture, in this description, the property of exact adaptation remains robust. However, and this is important, notice the level of activity. Before stimulus or after stimulus, activity is the same. That depends on all these parameters. That depends on KR population, that depends on this reaction rate VR, Key-B population. And if these populations change from cell to cell, then the value of the activity changes. Okay, so, but the fact that the system has precise adaptation does not change. So when you consider another cell, it will also show precise adaptation, exact adaptation. But at it may happen that it is adapting at a different value of activity. But consider that cell, pour in more attractant or remove more attractant, system will initially respond. But in the long time limit, when it relaxes to the steady state again, it will come back to the same level. And the main reason is the steady state activity does not depend on ligand concentration. So, while the value of the steady state activity remains a fine tuned property, because that will change from cell to cell, but the exact adaptation remains a robust feature of the network. Experimentally also people have seen this, that when they consider, when they look at precise value of the activity, that can be different for different cells. But every cell, it always show exact adaptation. Even this I am not showing here today, even the adaptation time scale, you can ask the question that, okay, I put in some attractant, then there is a sharp change. How long does it take for the activity to recover 50% of its steady state value? That is the definition of adaptation time. Even the adaptation time is a fine-tuned property. For different cells, that depends on all these details which are prone to cell fluctuations. So, even for that case, it is a fine-tuned property, but the exact adaptation remains robust. Okay, so this one last thing, there are few, this is a very simple description, there are few limitations of this. Here, this assumption that I have used, Kr works at saturation, if it so happens that VRR is larger than VBB, then the so then that means that you cannot neglect the substrate concentration for this case and retain it for this other case. So, then the saturation assumption for Kr breaks down. Secondly, yes, any question? Okay. So, secondly, here we have said that Kr works only on active receptors, Kb works only on active receptors. Suppose I slightly relax this assumption. I say that no, it is also possible for Kb to demethylate an inactive receptor, but with a very small rate, epsilon. Suppose I allow that. Then it follows that the exact adaptation is also lost by an amount which is of the order of epsilon. Okay, so this assumption is crucial. So these are limitations for this model. Okay, so that is, so for the next part of this lecture, I will switch to slides. Okay, there I will, so far what we were discussing, we were, please slide on kar dijiye. So far what we were discussing is this network, and we were discussing robustness feature, etc. But now I will turn to, I will tell you about more quantitative description of this network, which are actually used by people when they are doing simulations. Where, I mean, it would be a more quantitative description of this network. So, yeah. ये काम करता है ना दिस वन Thank you. नहीं जा रहा है सामने Okay, I'll do it from here. Come, Karan. Okay. Okay, so here I wanted to give you a more quantitative description of this diagram. So these are some of the points I have already covered. So let me just quickly zip through them. So the fact, so as I have said already, the E. coli chemotaxis is very well characterized. And the fact that it has these two modules in the network, sensory and adaptation, this is actually a very common feature in lot of other sensory networks. So that is another reason why this is so well studied. And although this network is fairly simple, I mean, okay, this may not look particularly simple, but compared to most other biological networks, this is remarkably simple. So despite its simplicity, this exhibits quite a few very rich and widely widely observed features of biological systems. One is robust adaptation, which we have discussed. Another is signal amplification. If you remember, we were talking about how receptors are clustered together, showing cooperative interaction, and therefore one single binding event results in activity switching of a large number of receptors. So that is signal amplification. And ultrasensitivity I have not mentioned. Ultrasensitivity actually refers to some switch-like dependence. Okay, people have observed experimentally that, remember I was talking about QIP binding to the flagellar motor and increasing their clockwise bias and causing the cell to tumble. People have measured experimentally the probability, the tumbling probability as a function of QIP concentration in the cell. Okay, and they have found a very switch-like dependence, like for a long time, when QIP concentration is increased from a small value to a large value, for a long time, tumbling probability remains almost zero, very small. Then suddenly, or zero or some very basal value. Then suddenly, within a very short range of change of QIP concentration, it quickly increases and then saturates to a large value. So this the range of concentration of QIP over which it happens is quite small. So this transition is very sharp. So this is called ultrasensitivity, and it is also seen in other biological systems, and this chemotaxis system is also something that shows ultrasensitivity. And some of this is recap, but yeah, it won't hurt. And the major players in this whole chemotaxis network, this is shown on the board also. So this is the transmembrane receptors and this cytoplasmic protein key A, which is the kinase which would autophosphorylate and cause the two reactions, so response and adaptation module. Key B is the demethylating enzyme, key R is the methylating enzyme, key W is the adapter protein that holds the receptor complex together, key Y is the response regulator protein, and key Z is the protein that is causing dephosphorylation of QIP back to QI. Okay. So this is the same diagram that I had shown. Now, okay, so these things I don't need to repeat once more. Now we will, so far we have said very qualitatively, look, receptors are found in the pole region in a tightly clustered form. But first it was observed by these people in 1993, they observed that chemoreceptors are forming very dense compact clusters near the cell pole. So then naturally the question came, what is the reason for this clustering? It was Bray for the first time and their collaborators who suggested that cooperativity could be helping the cell to amplify the signal. The conformational change of one receptor would give rise to conformational change in the neighboring receptors, which would be resulting in amplification of the input signal. Now, how to model this? So this is the most simple description one can think of. Describe it as an icing model. So imagine, so receptors form, I think this is where I mentioned it before, but chemoreceptors form homodimers. So I mentioned that there are 5 different types of receptors in the cell. They are present in different level of abundance, but similar receptors, they are not present in monomers. similar receptors, they come together to form dimers. Okay? And now these dimers, they are forming compact clusters. But anyway, so here the description is like this, that each dimer can bind to one ligand molecule, and we can think of these dimers as Ising spin. When they are active, we are calling it spin up state. When they are inactive, I am calling it spin down state. And apparently, I can think of it like that, that these Ising spins are on a lattice. Now, this idea of a lattice is not completely arbitrary, because people have actually seen in experiment this receptor array, they are organized in a cell in a form of hexagonal lattice. So, the lattice structure is there. In theory, people consider both hexagonal lattice and also a simple square lattice. But anyway, so you can, so this is the typical, this is the Hamiltonian of an Ising model. So, there is this exchange interaction between neighboring spins, and we also consider a magnetic field. How to interpret this magnetic field in terms of what we already know, I am coming to it. So, therefore, it is an Ising model of ferromagnetic interaction between the spins. Each receptor would like to have its neighboring receptors in the same activity state. If one of them happens to bind to a ligand, it would influence the others to switch their activity. And how strongly it can influence, that will depend on the value of J, how strong the cooperative interaction is. It will only act on the nearest. So, that is why I have put this Ij within angular brackets. So, so now I kind of try to find out some interpretation for the effective magnetic field. So, in absence of, so for that I considered just a single spin, a single receptor. So, it can be active or inactive. Let us say I describe the state of a receptor by two binary variables, activity and ligand occupancy. So, I say that the receptor can be activity, this A can be 0 or 1 if the receptor is inactive or active respectively, and this L can be 0 or 1 if the receptor is vacant or if the receptor is bound to some ligand molecule. Okay? So, therefore, I have a 4-state description of a chemoreceptors, and okay, I am coming to this picture, coming back to this picture later. And let us say the ligand dissociation constant from the active receptors and from the inactive receptors are given by Ka and Ki. Okay? Now, in absence, and another thing is, in absence of any ligand, the free energy difference between the active and inactive state would only depend on the methylation level M. I call it FMM. Let us say FMM is the energy or free energy coming from methylation states. Now, in steady state we expect, remember the first variable was activity, second variable was ligand binding, ligand occupancy. So, in the steady state we expect this ratio, which is the probability to find an inactive receptor bound to a ligand divided by probability to find an inactive receptor free. This probability will depend on this ratio, that the ratio of ligand concentration divided by dissociation constant for inactive receptors Ki. Is this clear? Anybody has any question? Everybody remembers the dissociation constant expression? Okay. In this is the second part where the receptor is active. Now, I am comparing the probability of finding it in active state and bound to a ligand and active state not bound to a ligand. So, this is ratio between ligand concentration divided by dissociation constant for active receptors Ka. And here for inactive receptors, what is the probability that ligand is bound and ligand is not bound? That probability, in absence of any ligand, that probability will depend on just their methylation level e to the minus FMM. Okay. FMM I do not know what is the form, I am just writing something. Together with all this, I have this normalization constant, that sum over all AL, PAL should be 1. So now you can actually solve this equation and you can write down the average activity of a receptor, that is probability that the receptor, average activity is probability to find an active receptor. So it is the probability to find an active receptor with or without ligand, that is P10 plus P11, and you can actually solve these equations to show that this has this particular form. Okay. So therefore, free energy difference between the active state and inactive state. Yes. Sorry, say it again. I could not hear the question.
You've written that the normalization condition goes over all A.
All A and L.
But in the next expression, is the A missing or is
here?
No, the next line.
Here. No, A is A. I am now putting in the value of A. So first digit is A, right? Remember here it is activity, ligand occupancy, activity, ligand occupancy. So this means receptor is active, free, active, ligand bound. Any other questions from this slide? Okay, so now we are calculating the free energy difference between the active state and inactive state. So P10 plus P11, that is the active state, and inactive state is P00 plus P01, and that is actually given by FMM. I can write it as FMM plus FLL, and if I just put in the values which I have solved for, it has this form. Okay. And average activity would be therefore simply 1 plus, assuming Boltzmann expression, e to the minus delta f inverse. Okay. So, so this is now explaining this picture that I had. So let me go through it. These are the inactive states, this color. So here this is the inactive unoccupied, inactive free, and the energy difference between these two is log of ligand concentration divided by Ki. Given that if I would like to write the ratio of probabilities as exponential of something, so the energy difference would be this. Similarly, for active states, it is log of Ka by L, and this is the energy difference between the active and inactive state in absence of any ligand. This is FMM. This is a pictorial way of presenting what we have just discussed. So therefore, we derive so this is an important equation. We derive the effective free energy difference between the active and inactive state of a single receptor. Turns out it is a function of the methylation of the receptor and it is a function of the ligand concentration. Ligand concentration dependence we have already written down, but we still do not know what is FMM. So, okay. So therefore, this quantity actually plays the role of an effective magnetic field. If you go back to the Ising model, consider a single spin, then you do not have to worry about any exchange interaction. So now the energy difference between the upspin and downspin state will just depend on the magnetic field. Okay? So this is what it is, energy difference between active and inactive state. So this plays the role of an effective magnetic field. Yes?
Is this why we actually take the form e to the power minus m?
Is this why we?
Yeah, the form.
This is an assumption. Yes, we are writing it in this way. We are okay. This is the energy difference. If this is an energy difference, then the probability will be e to the minus energy difference.
That's the motivation that we took the form exponential of minus something.
Yeah, we will assume that these activity switching, these are happening very fast. So they are almost always at equilibrium. So therefore, if there is an energy difference between two states as E, then e to the minus beta delta E would be the respective probability ratio. That is what we used. Another important thing here, which, yes. Oh, it is all written in units of kBt.
Okay.
Yeah. So another important thing is, Ka and Ki. I started them with as some arbitrary values. Okay, these are arbitrary, these are dissociation constant. But now look at this expression. If L is much larger than Ka or much smaller than Ki, then this thing becomes independent of L, because Ki is anyway much, Ka is smaller or Ki is, just one second, inactive state, yeah, Ki is smaller, Ka is larger, I think, right? Am I saying the opposite thing? Okay. So, anyway, so if the receptor, so inactive states prefer the receptor, so dissociation constant would be larger. So, Ki is larger, Ka is smaller. So, if imagine that if L is much smaller than Ki, or if L is much larger than Ka, then these things become independent of L. Okay? In one case you can drop, it is much smaller than 1, then also this term becomes 1. In another case it will be much larger than 1, then you can drop the 1 and L gets cancelled. So therefore, this means that if L goes, the ligand concentration goes beyond a certain range, the free energy difference is not dependent on ligand concentration anymore. So this sets the range of sensitivity for an E. coli. That it tells you that if the ligand concentration is too small or too large, the bacteria cannot sense it. What do you mean by too small or too large? That is set by these values Ka and Ki. Okay? Now, therefore, if we continue with the Ising type of description, then imagine that you have a total number of receptors given by Nt. The activity of each receptor I, which is a set, which is a number between 1 and Nt, in the cluster is given by Ai, that is, that could be 0 or 1. Each neighboring pair, they interact with each other via this exchange interaction, and there is also a magnetic field, which this exchange interaction is independent of anything else. It is some internal dynamics of the receptors. It tells you that, okay, I would just like to have, similar activity states around. But then how do you influence that? This is coming from this term, that you add more ligand or you remove more ligand. That should somehow shift the free energy difference between the two states. That is coming from this effective magnetic field term. Similarly, as we have also seen, right, that the internal, methylation level of the receptors has something to do with activity. That is how we were all the time describing this negative feedback, etc. We were talking about these methylation sites which are like buttons, you push them, activity goes up. So those things has to feature in the model. That is done by this particular term, the second term. It is a function of methylation, the internal degree of freedom, as well as ligand density, ligand concentration, which is from the extracellular environment. And if you are given a set of activities A1, A2 up to ANT, you can actually use this Hamiltonian to calculate the energy of that configuration. Any questions? One thing is, for the purpose, the most important, for the purpose of simplicity. Okay, this much we have to consider, because we do find, otherwise we would love to even get rid of any interaction. That is easier for us, but we have, experimentalists have seen cooperative interaction, signal amplification, so we have to introduce something. So here we do that by using this nearest neighbor connectivity. I will shortly introduce another way of modeling this clustering, the cooperative interaction, which doesn't involve any nearest neighbor connectivity. Yes?
Like in the Ising scenario, when we can write down magnetization susceptibility as derivatives of the free energy, can an analogous thing be done over here? Are there analogous quantities?
We can do, but the thing is, see, if we are describing this as exchange interaction, if you are describing this as effective magnetic field, then we can define all these things. But the question is, are those things experimentally meaningful? So there you have to, do some checking that whether those things are experimentally measured, whether particularly. biologists, I am not saying even biologists, unlike my previous speaker, but anyway. So whether that is, whether they would be interested in looking at those quantities. Okay. There are possible generalization of this model. One is you can consider mixed receptor clusters. So we talked about 5 different types of receptors. So they are, here you can consider that there is a chain of receptors, or there is some lattice arrangement that some of the receptors may be of a different type. Maybe you are mixing serine sensing receptors and aspartate sensing receptors, TSR, TAR, possibly, one possible way. So there you have to, I mean, there in that case would mean, what would mean that suppose you are placing the cell in an environment of serine chemical, but in the cluster arrangement that you have, there are some aspartate sensing receptors also. Okay. For how do I handle those cases? For those receptors, I will assume that their free energy does not depend on L at all, because they are insensitive to serine. Okay, so for those cases, I will not have this L. So for those cases, free energy difference between the active and inactive state for that particular receptor, which is like a, I mean, some other, coming from some other family, for the, that will only depend on their methylation level and not on anything else. Okay. Remember that the cooperative interaction is still there. So even though they may not be sensing that particular chemical, just because their neighboring ones have sensed it and changed their activity state, they might still change their activity state. Okay. Acha. Another thing is, if you are considering mixed receptors, then of course you also have to consider the possibility that the exchange interaction J will be different between different, I mean there are some different species, they will not give, I mean different families have different level of tolerance like for other type of people. So one receptor, it may say that okay, it absolutely hate anybody who is in a different activity state, but some other receptor from some other family may have a slightly higher tolerance than that. Anyway, so another possible generalization is all these things that J, A, K, A, K, I may in turn be a function of the methylation level, which can be very complicated, and but sometimes it is needed to find a quantitative agreement with experimental data. Okay. But we will not, so right now we are not discussing quantitative agreement, we are just, I am just giving you some flavor of how to quantitatively model some signaling network like that. Now coming back to, yes.
So at a time, how many receptors are in cooperative behavior, like hundreds or tens?
That entirely depends on the strength of cooperative interaction you take.
No, not the strength, like how many of them are in a cooperative behavior? I mean, how many of them are in the, so you're considering Ising model kind of thing, right?
Yeah, yeah, it's the same thing, right? Exactly, I am giving the answer in terms of Ising model, that it is the strength of the cooperative interaction and it is the temperature. So that will depend, that decides the correlation length in the system. So that would be roughly the, I mean, cluster size, so to speak.
Okay, thank you.
Okay, so here it is coming back to the question he was asking, that this is another way to model the cooperative interaction, which is a simpler way than the Ising description. It is called all or none model, or MWC model, named after these 3 people. So it says that instead of looking into each receptor dimer individually and modeling them as an Ising spin which can flip, I would break the system into some subcluster. Each cluster I call a signaling team, and all the receptors who are part of one cluster are very tightly coupled. So they all switch their activity state in unison, and receptors which are part of different clusters, they can change their activity state independently. Okay? So this is the picture of MWC model. So here red and this green, these are 2 different activity states, let's say active and inactive, And so you see everybody within that cluster, within a cluster has the same color, same activity state. And this is the corresponding situation for an Ising model, where you still see clustering, that reds are, I mean, kind of clustering together, greens are clustering together, but it is not like a very clean boundary. Okay. This one?
Yeah, because
Yeah,
each
within a cluster, yeah. If you consider one cluster as one unit, then there is no.
It's like a j equal to 0.
Yeah, but within a cluster, j is infinity.
That's fine, but I mean, like, I redefine my spin as a cluster.
Then you can, then they are independent.
They are just.
Yes, but remember, the main idea of clustering was signal amplification. Signal amplification is still done here, because the cluster size.
Yeah, but
that
these are
is-
same sizes, right?
They're same sizes.
So it's just a strength of the spin is.
Strength of the spin,
I mean,
yeah.
I just put a.
That's right. That's
Yeah,
right.
right?
Yeah, this is a
Okay.
simpler description. That's right. But I mean, the reason I said it is cooperative interaction we have to include, because signal amplification I have to include in my description. This is a simpler way of including that. Okay, without considering the spin-spin dynamics separately, I would. But as Sanjeev pointed out, if you define one signaling team as one unit, then there is no, between two different signaling teams, there is no cooperativity. Okay. So in the MWC model, or this all or none model it's called, the degree of cooperativity is simply given by n, the size of the cluster. Okay. So in comparison, for the Ising model, degree of cooperativity is given by the correlation length. Now for the MWC model, free energy difference between the two states, here the two states will be all active, all inactive within a cluster. That is simply n times the free energy difference for a single receptor. And so therefore, average activity is given by e to the minus n delta f inverse, and delta A therefore has this form, where L, this L variable I have introduced, L within square bracket means ligand concentration. The simple L variable is e to the minus n FMM, the methylation part of the free energy. Although it may seem that this MWC is a it's very simple description, it's almost trivial, but it turns out that it is not so bad when it comes to explaining your experimental data. So for the first time, experimental data became available after this experiment, which was performed by Sourjik and Berg in 2002. They for the first time measured the activity of a receptor cluster using some freight kind of technique. Yes, and in live cell, yes. MWC. Mm-hmm.
Aren't we losing information on the system? It's like we are flipping on symbols.
Of course. Of course, but this is what we were discussing in this slide, that depends on what experimental data you are trying to understand. Okay, if you are trying to see cooperative, I mean signal amplification, then MWC model does pretty well. But there are some measurements which might involve individual dynamics of the receptors. For those things, you will this doesn't give good agreement.
And that also depends on the how we actually take the cluster. What's the form of the cluster, like hexagon or square or?
It doesn't because actually it is hexagon, but turns out that people have also done things on a square, and they found the agreement is not so bad. What is important here is the cluster size, how large teams you should take. That is often read off from the data. You calculate something, and n is often, the cluster size is often used as a fitting parameter. Okay, so I will show those things. Okay, so this was the first time they actually measured the activity in a live E. coli cell, and they used different types of stimulus. They used wild type cell as well as some mutant strain, and they generated lot of data of kinase activity. And for the first, after 1 year, this Melo and Tu, this group, they explained those experimental data using Ising type model. When they tried to experiment those experimental data using Ising type model, they concluded that it can be explained only with mixed receptor clusters. You cannot use this. Mixed receptor clusters is when in a receptor cluster there are some receptors from serine family, serine sensing, some are aspartate sensing, so those type of. So when you have a mixed receptor cluster, then some of the receptors will not have the ligand part in their free energy because they are not sensing the ambient concentration of that ligand. Then in this paper, Sorjik and Berg, they considered different types. And by that time they had mastered quite a few techniques on how to change expression levels of different types of proteins in the cell. So they considered different levels of expressions for kinase, for key R, for key B, and they looked how does it change the activity. Okay. And they had that was a quite rich experiment because they kept on, they changed key A concentration, for example. They changed the expression level of key R, different proteins, and they generated the activity, and it turns out that using MWC model with homogeneous clusters, they could explain those data quantitatively. So this shows that MWC model also is very simple. It's not so bad after all. It can actually quantitatively explain the experimental data. And since I would go for simplicity, although I may think that, no, I am losing this, I am losing that, but as a theorist, I would I would like to go for the simplest possible description to explain the phenomena that I am interested in, okay? And these people in 2005, they developed the MWC model with heterogeneous clustering. Okay, this is just to give you an idea that these models are, this seems simple, Ising model seems very simple, and MWC model is even simpler than that, but they, so far as experimental data explaining is concerned, they are not so bad. Okay, then the remaining half an hour or so, I will explain some other things about the adaptation. So we have seen that we talked about sensory adaptation, and we discussed about robustness versus fine tuning for exact adaptation. And so then we discussed how fine tuning might be unreasonable for a noisy biological system. So then Barkay-Libler model was introduced, and we discussed it, which says key R works at saturation and key B only acts on active receptors. Using these two assumptions, you can actually find some description of robustness as a, adaptation as a robust phenomena. Turns out later studies showed that these assumptions are sufficient but not necessary for exact adaptation. For example, key R does not have to work at saturation as long as it favors inactive receptors as its substrate. This very important work by Melo and Tu showed this. So therefore, not only we are saying that demethylation enzyme preferably works on active receptors, I am also saying methylation enzyme also works preferably on inactive receptors. If I include this, then actually I don't need key R to work at full saturation. I can still get exact adaptation. Okay? So, however, we are all the time talking about exact adaptation, how robust it is, how great it is that these simple models have derived it, etc. But the question remains, what is the benefit of exact adaptation? Okay, one thing we discussed, that exact adaptation allows the system to respond to multiple doses of attractant. But is there anything more to it? So what I will show that it actually effect of exact adaptation is it helps the system to maintain a high gain. So what is a high gain? High gain is, it is also a measure of sensitivity, that if by giving a little input I can elicit a large response from the system, that is called the system is operating at a high gain. Okay. So it turns out that exact adaptation actually makes sure that the system is operating in that mode. So to show that, we start with a background ligand concentration L0 and average methylation level Mi, and then the receptors, I am using MWC model, they have the average activity which is given by this. Here this L0 is e to the n Fm Mi. Okay. So I have one L0 within bracket, another L0 without a bracket, which is this e to the n, this methylation energy. Okay. Now let us say this is the average activity, I call it A0. Let us say I change the ligand concentration from L0 to L0 plus delta L. So immediately after that change, there would be an immediate change in activity. That I can calculate directly from this formula. Because it is an immediate change, methylation part does not have time to respond yet. So all I have to do is to wherever I have ligand concentration, I will put in this new value. Okay. So then the change in activity would be, I write the same thing, instead of L0, I write L0 plus delta L everywhere, here, here and here, and I subtract from it the pre-stimulus activity A0. So I have used the same L0 here, the methylation part is unchanged. Okay. Now, if the change is small, the change in, if delta L is much small than the ligand concentration, if I have added only a tiny little bit of attractant, then I can do a Taylor expansion of this, keep only the first order term, and then delta A has this approximate form. Okay, I am not doing the algebra, but yeah, delta L A has this approximate form. You look very confused, is it okay? Yeah, okay. Okay. So here you see, and you can see it from here. See, whenever this L occurs, you have this exponent n. Okay, n is in the exponent. So when I am doing del L of this quantity, n comes in the front. So this is clearly, it shows that the whatever response I have, that just gets multiplied by n. Okay, so the cluster size. So this is signal amplification and just directly. Okay. And it also depends, the delta A also depends on A0, the pre-stimulus activity, and it is 0 if A0 is 0 or 1. It is clearly following from this form. So therefore, if A0 is very small or very large, you see A0 is what? A0 is the probability to find the receptor in an active state. So therefore, it cannot go beyond 0 and 1. So if it is very small or very large, then the response will be very small, almost response will be vanishing. So the maximum response is obtained somewhere in the middle. Exactly at which value I still do not know, but somewhere in the middle. However, here it seems that if I maximize A0, then that depends on this A0 is it depends on L0, this pre-stimulus background concentration of ligand. And therefore, if the ligand concentration is changed, then delta A will also change. So even if I can find what is the maximum value of delta A, it will be a function of the background ligand concentration. And as soon as that concentration is changed, I don't have the maximum response anymore. I am not operating at the high gain regime anymore. So this is why we need exact adaptation, to restore the activity back to A0 in order to maintain high signal amplification or gain. So immediately after, so it seems every system, what it says, what this equation says, every system has an optimal value of activity at which it is most sensitive. Now if I put in more ligand, and how do I measure sensitivity? By adding little bit of ligand and seeing what is the response it is giving me immediately. That is the measure of sensitivity. So if it so happens that if I add more ligand and if the activity is changing, then actually I am getting away from that region of high sensitivity. So next time I add more ligand, the system will not perform very well. So this is the function of exact adaptation. This is the usefulness of exact adaptation. It is every time bringing the activity back to the value such that before I add my second dose of ligand, third dose of ligand, every time I am operating in the most sensitive range. Okay. So this is what I have written here. Essentially, adaptation drives a very slow change in M and consequently a change in L naught without bracket, which balances the change of the stimulus and restored the activity back to A naught. Okay. So this is actually a benefit of exact adaptation, that it is not as simple as okay, it is ready to receive more, but the system is tuning itself to be at the activity where it can respond in the best possible way to the input given to it. So this is a pictorial way of saying it. So imagine this was my initial dose response curve. This is activity, this is the input ligand concentration. So suppose A was my, okay, look at this picture. Suppose I started with L naught, then I have increased L naught and I have the new value is L. Okay, this is the step addition of stimulus. And this is what activity does. As soon as you start it, activity was initially at A. As soon as you add more ligand, it drops to B, then it creeps back up to C, which is the same activity. So here I have identified these points. What happens is, it starts from A, suppose it was here, A was here. Then you add more activity, it is a fast response, this is where B is. But then activity increases and reaches C, and now this is my shifted dose response curve. Now the system is actually operating on this curve, not on this one. See the mechanism? Because when I am going from B to C, I am getting up vertically. So the input concentration is not changing anymore, because after I have added the ligand, I am not touching the ligand level. But with the same ligand level, I would like to get to the same value of activity. So therefore, now I am operating with a shifted dose response curve. Adaptation, this is what adaptation does. Adaptation corresponds to a shift of the response curve such that adapted activity at the new ligand concentration returns to A naught. Who doesn't understand this? This is an important thing. So make sure you are perfectly comfortable with it. You want me to repeat, you tell me, I will repeat. If you want to ask a question, ask a question. Yes. Repeat, okay. Yeah, so what I was saying that you could follow this, right? That this is my average activity, which is a function of ligand concentration as well as methylation. I change the ligand concentration. This is my change in activity. Maximum gain means this change in activity should be as large as possible. So if I write down an expression for the change in activity, I see it will vanish if the activity is close to 0 or 1. So therefore, somewhere in between it would be largest. But that point is a function of the background ligand concentration. That is the point of worry, because every time I add a ligand, it seems I am shifting away from this this best operating regime. So that is why I need exact adaptation such that even after addition of the ligand, my activity comes back to the same value A naught. And this is what I have explained from this curve. You add a step stimulus. So this is what a typical time variation of activity looks like. You start from A, quickly drop to B, and then you raise back up to C. In order to make sure that this AB, this drop is largest, because that is the measure of response. In order to make sure this drop is largest, what I do, this is A, this is, suppose this is where I started, this is what my background ligand concentration, and this was my activity. Then I change my ligand concentration to this point, suppose. Then activity will roll down and and it will take the value b, and then exact adaptation will bring it up, and now I have a different dose response curve. You can ask, okay, this way I have generated only one point on the dose response curve. How did I get the remaining part of the line? Who can answer that question? This just gives me this point C, but in order to trace out this curve, I need all these other points also. So how can I get there? No, but this is the steady state activity. Here I am plotting the steady state activity. So no, so it just means if I am starting from A, I will only generate points which is at this level. If I start from a different value, I mean if I start from a different initial activity, then I will generate this curve. Okay, so it's not so important. So, so therefore, when the system adapts to the ambient ligand concentration, this is post-stimulus state, then the L0, this is the methylation dependent L0, it has this form. And therefore, using this value, you can, so therefore given A0, and I know all this, so L0 can be calculated from this, and then using this value of L0, you can predict the immediate response. You can predict the delta A, and you can directly check it with simulation. So activity A, L0, this is this activity is function of both final and initial ligand concentration. So this is the activity right after the ligand concentration is changed from L0 to L. This is given by this expression, and you can actually measure this thing in experiment, because this is what I am measuring is what is the drop in activity. I am measuring the activity at the point B, and here from this expression I have an actual formula for that, and here I have only 4 parameters N, A0, Ka and Ki, and I can use this to fit the experimental data quantitatively, and the good thing is none of these parameters are arbitrary. They have a very clear biological significance. N is the cluster size, A0 is the pre-stimulus activity, Ka and Ki set the range of sensitivity. So using these 4 parameters, I can fit the experimental data. So this is one actual experimental data. Here, these empty circles, they actually give me the adapted activity, and these different dose response curves give me different values of L0. Okay. So for example, so suppose this is, I started with 0 millimolar background level. Then here this is I have plotted it as a function of final, note that this is methyl aspartate. Remember yesterday I was telling you that sometimes you consider some chemical modification of a nutrient to make them into non-metabolizable chemical. So often experiments are performed using that. This is one example. So here, just to make sure you understand this plot, this is the last thing I want to say. So, okay, I still have time. So, here different curves correspond to different values of the background concentration. The x-axis is the final amount of ligand that is present in the system, final ligand concentration, and this one gives me the immediate value, experimentally measured, the immediate value of activity. Right after I add the ligand, what is the activity value that I am measuring? These empty circles are experimental data, and suppose I started from here. Then I added some, more ligand, and then the change in activity, the final activity is here immediately after adding the ligand, and then finally the system will go back up, and this is my new dose response curve. So you see, for every after every experimentally measured line, I have a single line with a single empty circle. So this is the shifted dose response curve. Okay. So here I have 0 millimolar, 0.1 millimolar, 0.5 millimolar, 5 millimolar. So these are the different background levels of attractant that I started with, and by using this method of exact adaptation, I traced out this curve which tells me that these are the adapted values. And in fact, when you fit these are the values you get. That n turns out to be 6. Somebody was asking what is the cluster size, that this data shows that is close to 6. Ka turns out to be 18 micromolar, Ki 3 millimolar. These are the range of sensitivity. E. coli can sense anything between 18 micromolar and 3 millimolar, and A naught turns out to be about 1/3. Okay, that's all I had to say. So if you have any questions, you can ask. Yes. 6 dimers. Hmm?
The coarse grain model that you were looking at, its size was that the coarse grain model that you were looking at, the size of the coarse graining is 6.
Which coarse grain model?
The one which was like the water model. I forgot the name.
MWC, all or none?
MWC, yeah.
Okay.
Yeah.
Okay, so in an MWC model, you can actually play with any, you can just decide. But here, that's what it means, that size of the cluster, size of that would be 6 if you fit it from the experimental data. Okay?
Ma'am, I didn't get this part of dimers. So when we are taking this as one Ising spin, are these like two
dimers?
So these are dimers?
Two receptors come together to form homodimer.
But they could be of different species, like there are 5 species?
No, dimers are always homodimers. Same type of receptors come together to form dimers.
Okay.
But they can be showing cooperativity with other types of receptors also.
Okay. Thanks.
Yes.
A bit tangential, but is there any understanding or interest in like the energetic cost of this entire process of adaptation and the efficiency and things like that?
Energetic cost means?
I mean, the whole process is in non-equilibrium, so there has to be some sort of chemical driving within the cell to make this happen. So the energetic cost of that and how efficient it is and things like that.
Generally, efficiency in this case is measured by measuring their sensitivity. How much energy does it spend? I have not seen anything related to that. It is because these cells are okay. So I don't know. Maybe because they, yeah, of course. I mean, they need nutrient. They metabolize the nutrient, but they are like self-driven. So therefore, yeah. Generally, it is measured how sensitive they are. So based on that, the sensitivity is generally measured. Yes.
Is it always ferromagnetic-like interactions between the receptors?
Yes, because you see why it is needed for signal amplification. If you are flipping and others are flipping in the opposite direction, then actually ultimately there is not much change in activity. So therefore, antiferro, if I am thinking of it this way, clustering helps in signal amplification. I always need a cooperative interaction, ferromagnetic type of interaction.
Yeah, but each receptors are sort of specialized for certain ligands, right?
Each receptors are specialized for?
Certain types of ligands.
Certain types of ligands, yes.
So, isn't it more efficient to not use
those
receptors?
Actually, no. Yeah, the thing is, there can be some receptors sitting in a mixed cluster. There can be some receptors sitting in a neighborhood of other receptors, other family of receptors. It may not have anything to do with that ligand, but just because others are flipping, it also has to flip because of this cooperative interaction. The strength of the cooperative interaction will also be different between between two receptors coming from different families. That can be different, but still that cooperativity is there.
So is it like if a receptor does not have an affinity for the particular ligand, it could still, just because it's active, it could still activate other receptors which are not, which might not be receiving ligands at the same intensity.
Sorry, say it again.
So
If a receptor is not particularly binding to that ligand, even then
even then, just by the fact that it's active, it helps.
Exactly. Exactly. They can still help in the signal amplification process, so which is good for the cell. Even if you don't like it, okay, why don't you just do what I tell you to do, and that way everybody can benefit.
But that raises an interesting point, right? So is it like, for example, prone to be just activated by noise? So for example, is a transient binding with not proper. There's a transient binding with not the appropriate ligand. So it just about attaches and then goes away, and this causes a false detection. So isn't it becoming very noise?
Yeah, and there are works on that where people have shown that sometimes you can get a noisy input signal, okay, and then if there is too much of signal amplification, there is too much of noise amplification as well, okay. So in that case, people have shown that there is actually an optimal size of the cluster size, which I wanted to describe it in tomorrow's class. There is an optimal size of the cluster beyond which cooperativity does not help. And that depends on how much noise are present in that signal.
So if you increase a ligand concentration slower than the response time, then presumably the, what we call sensitivity will not change, right?
If you change the
ligand concentration very slowly, then I think it will just stay constant, right?
Okay, so if you assume that, okay, I change it very slowly such that the adaptation even slower than the adaptation time scale, yes, then there won't be any change. But adaptation is very small. Adaptation process is very slow.
In wild, like I'm assuming that they do not come across a sudden change in concentration like abruptly. It must happen slower.
Not necessarily. Not necessarily. They can suddenly find themselves in presence of some source, which is actually, or there could be some nutrient which is diffusing. And in fact, often it helps, there is some nutrient or some attractant which are perhaps not even very stable, they are degrading away. Okay, then the cell would like to get to them as quickly as possible. So all those things are there. Yeah. It's not like in wild type situations you only have very slow things, you always are in equilibrium. So it's often the opposite of that.
Actually, Harish's question made me think about an interesting point. So like for you it's ferromagnetic because I guess E. coli does not need to know which of its receptors has been activated. It just wants to know has the receptor been activated or not. But in organisms like us, so for example, like in our visual system, for example, we'd like to know where exactly a particular light spot is coming from, right? So we would like to localize. So there actually it turns out lateral inhibition, for example, in all the human sensory apparatus, lateral inhibition principle is at work. So if a particular receptor is activated, it tries to suppress the activity of the neighboring receptors, which presumably also might be getting activated because they're receiving some of the residual signals. But in that case, you have this entire blob of receptors which are activated, which kind of, you lose spatial resolution. So whereas you want to like pinpoint the exact location, so then lateral inhibition is generally the mechanism which the human sensory apparatus uses. So it's kind of interesting.
So you are saying too large an amplification acts as a distraction.
Right.
When I really want to focus on something.
Right. So for resolution you need, in some sense antiferromagnetic, whereas for sensitivity you need ferromagnetic. So
That's
maybe
right.
there's like an interesting way of combining.
That's right. Yes, yes. That's an interesting point. Yes.
Then again the next receptor will be like in on stage.
No, so here what you're saying is that, so let's say there's a signal which activates some local region. Right? Now the thing is that if within that local region, all the receptors are trying to inhibit each other, so then eventually only one will win, the one which is presumably receiving which is in the focus of the signal. Okay, so then you are managing to exactly pinpoint where exactly the signal is located in the topographic mapping that you have of the external world in your visual system. Okay.
Maybe even our neural networks may work like that.
Exactly. So our neural networks actually uses.
So you say, yeah. So even when we receive any input, we want to, and this is something we are always doing in academics, right? We want to think in the right direction, not in. Okay, so if there are no other questions, so I'll stop here. In tomorrow's class, I will consider what happens when we have noise present in the system, both external and internal noise. So we would like to see what happens, how noise affects the chemotactic performance of an E. coli cell.
So we'll have tutorial at 4:30. I think today all of you are there probably. Yeah. I just want to make a small announcement because Saturday, Sunday we have holidays, right? So all breakfast, lunch, dinner will be served at the academic guest house for the people who are staying in the guest house. So in case some of you plan to go out and see one or two going out is okay, but suppose you plan to go out in large numbers, maybe just send an email to Gayatri, this thing, so that there is no large amount of food wastage. I mean, if you plan to have dinner, breakfast, lunch, it's good. It will be anywhere there, but so I think there are 55 staying there. If out of 55, 30 just goes out and like the food is prepared for 55, then it's like a large wastage. In case you plan to go out Saturday, Sunday, just send an email basically. Yeah.